I alpha times cosine, actually, not just cosine, 2 cosine of delta. What this looks like in the context of our discussion of wave packets is if we have an axis there, we have this cosine factor, and it's the cosine of delta. If k1 and k2 are near each other, this will be a small number. This will also be a relatively small number. So delta evolves much more slowly with space and time than alpha. So if I was going to draw this wave function, I would have some slowly varying envelope like this, and superposed on top of that, multiplied by that slowly varying envelope, is e to the I alpha, which is the sum. So if k1 is close to k2, this is going to evolve much more rapidly. So my overall wave packet is going to look something like this, where you have zeros and areas with large amplitude, areas with small amplitude, areas with large amplitude, areas with small amplitude. As time evolves, this wave packet will propagate. And if what we're interested in is the velocity with which the overall packet propagates, you can consider a point on delta, not a point on alpha. If we're interested in the velocity with which these rapidly moving peaks, rapidly oscillating peaks evolve, then we would look at alpha. But since what we're interested in now is the wave packet, we want to look at delta. We want to look at the slowly varying envelope, how quickly the slowly varying envelope moves. Now, I haven't actually constructed a fully formed, physically realizable wave packet here because I have this cosine term, which again extends all the way from minus infinity to infinity. But hopefully, conceptually, you can think about this as a sort of rudimentary wave packet. The question then is, how fast does the rudimentary wave packet move? Well, if I look at delta, and if I assume that k1 is near k2, we can see how that works out. So what I'm looking at here is delta is equal to 0, say. The same sort of argument that I was using to determine how fast a feature on a single wave moved, setting this delta equal to a constant, not caring what the constant was, and setting it equal to 0. What I get then is k1 minus k2 over 2x being equal to h bar over 4m, and then k1 squared minus k2 squared, I'm going to look at this as the difference of two squares, which I can factor, k1 plus k2 times k1 minus k2. I can then cancel out this and this, and what I'm left with is just x over 2 equals to h over 4m k1 plus k2. If I assume that k1 is about equal to k2 then, I can pretend that this is some effective average k bar. If I write that out, sorry, this is 2 k bar, twice k bar, since I have k1 and k2, and they're added together. I can then look at this. I have a 1 over 2 here, a 1 over 4 here, and a 2 here. What I end up with at the end is just going to be x equals h bar over m times k bar. This is different than the expression we got before. K bar now is going to be our average k, h bar over m to copy that over, and our k was root 2m e bar now for k bar. Instead of k bar, I'll have e bar for my average. And then I have Planck's constant. I can cancel out Planck's constant in the denominator. I can again push my mass into the square root here, and what I'm left with then is root 2e over m times time. I forgot my times time here. All of these have a times time. So x equals something times time. This is our velocity. So here, for the wave packet velocity, we get root 2e over m. This is the classical velocity. So, problem solved. Whereas the features on each individual peak, for instance, in our wave function, traveled at one velocity, the overall wave packet traveled at another velocity. For the case of this particular wave packet, or wave packets in general, the wave packet itself travels at the velocity you would expect, except I have to be clear here now. Let me rewrite this. The velocity we get for a wave packet now, this is only approximate, so I should write it as approximately equals, and it's not twice the energy, it's twice the average energy divided by mass in the square root. So this is not exactly the classical formula because now we don't necessarily have a single energy. If we had a single energy, we would be stuck with one of those solutions to the time-independent Schrodinger equation, which have definite energy. In the case of this free particle, those definite energy solutions extended throughout all space, and that was a problem. So we don't actually have a definite energy, so we'll have some spread in energies here. And if you have a large spread in energies, you'll effectively get a large spread in velocities. And what starts off as a wave packet will not stay a wave packet very long. It will propagate at different speeds. Different parts of the wave packet will propagate faster than others. But at any rate, what this actually looks like, to make some visuals here, and I couldn't hope to draw this accurately, but if we have some wave packet at time t equals 0, delta t, 2 delta t, and 3 delta t, it's going to propagate gradually. You can see the disturbance of this wave moving to the right. Now I've drawn solid, thick lines here behind it to designate the motion of the overall wave packet. The overall packet is moving at a speed more or less determined by the slope of these thick black lines. The thin gray lines identify features. For instance, this peak becomes this peak, becomes this peak, becomes this peak. This peak is traveling at a more slow rate than the overall wave packet and is essentially sort of falling off the back of the packet. It's decreasing in amplitude as it goes. The slopes of these lines are different, meaning the features on the waves are propagating at a different speed than the overall wave packet. This is actually a general feature of many waves. It's not something we hear about very often in everyday life because we never really think about whether there might be a difference or not. Plus, most of the common waves that we work with, like sound waves for instance, don't have this property. But if you look closely, for instance, if you drop a rock in a still pond, the small-scale ripples actually behave with this different velocity. In that case, actually, the features on the wave move faster than the overall wave packet. So in that case, you could view this as sort of time reverse, where the features start at the back of the wave packet and propagate forwards. But this is really the question of what's called group velocity and the question of phase velocity. The phase velocity refers to the features in the wave, whereas the group velocity refers to the velocity of the wave packet. This is not a wave mechanics course, but there's a lot of interesting math that can be done with this. The group velocity and the phase velocity being different is one of the more interesting features of, for instance, propagation of electromagnetic waves in plasmas in space. So if you're interested in radio astronomy, for instance, you need to know about this in very high levels of detail. To give you a better feel for what this looks like, here's an animation. What we're looking at now are the real and complex parts, shown in red and blue, respectively, of a hypothetical wave packet that might represent a solution to the Schrodinger equation. It doesn't actually represent a solution to the Schrodinger equation, but this is the sort of behavior we're looking at. If I track a particular pulse, say this one, I'm moving my hand to the right as I do so. Here. But I'm not moving my hand to the right nearly as fast as the overall wave packet is propagating. So the overall wave packet is propagating at effectively twice the speed of the individual features on the wave. So this is what wave propagation might actually look like for the Schrodinger equation. You can construct wave packets like this. If you add the time dependence, then you can determine how the wave packet will propagate, how it will spread out, how the individual wave features will move, and you'll know effectively everything you need to. To check your understanding, here are a few true or false questions. Don't think that because they're true or false, they're easy. Think about these in detail. We've already met the Dirac delta function a couple of times in this course as examples. So it's good at this point, since what we're going to be discussing next is the Dirac delta function as a potential, to discuss the general properties of the Dirac delta function, how it works from the mathematical perspective. What I want you guys to think of when you think of the Dirac delta function is the limit of a distribution. The Gaussian distribution, for example, rho of x is given by 1 over the square root of 2 pi as a normalization, sigma, e to the minus, say, x squared over 2 sigma squared. The limit as sigma goes to 0 of this function gives you something that is very much like the delta function. This is not the only way to define the delta function, but if we start with, for instance, this purple curve here at large sigma, and this orange curve here at small sigma. As sigma gets smaller and smaller, the distribution gets narrower and narrower and taller. As sigma gets smaller, for instance, the dependence here in the exponent of e to the minus x squared gets faster and faster since I'm effectively multiplying the x squared by a larger and larger number. And the normalization constant out front, 1 over root 2 pi times sigma, gets larger and larger as sigma gets smaller and smaller. So thinking about this as the limit, in the limit, we have a distribution that is infinitely narrow and infinitely tall. It has absolutely no support for any values of x other than, say, x equals 0 here. So this would be, say, delta of x as a distribution. You often see delta functions written as, in terms of more conventional function notation, delta of x is equal to 0 for x not equal to 0 and infinity for x equals to 0. But this isn't a sufficiently accurate description because it doesn't tell you this property that the delta function is the limit of a distribution. It has specified integral. So you always have to add an extra condition here for something like, for instance, something like the integral from minus infinity to infinity of delta of x dx is equal to 1. That essentially sets the specific value of the infinity here such that the integral equals 1. But thinking of it as the limit of a distribution is essentially the actual definition of the delta function. Knowing that the delta function acts like a distribution allows us to do things like calculate integrals with delta functions. This is where delta functions really shine. If you have an integral of minus infinity to infinity of any function, f of x, multiplied by the delta function, if we think of this as a distribution, this is effectively the expectation of x, of f of x, the expected value of f of x, subject to this distribution given by the delta function. Now, since the delta function has absolutely no support over any values of x other than x equals 0, essentially what this is telling you is the expected value of f of x where the only region that we care about is the area very near 0. So this just gives us f of 0. Thinking about this in the context of a distribution, if we had a distribution with some very narrow width, if this width gets extraordinarily narrow, then no matter what f of x does out here, we don't care. And as the distribution becomes extraordinarily narrow, we're just zeroing in on the behavior of x over this region, which makes f of x basically look like a constant. And you know, the expected value of a constant, like if I wrote this as the expected value of f of 0, it wouldn't matter what the distribution was, it would just give you f of 0. So this is the same sort of concept. The infinitely narrow distribution effectively just pulls out the value of f of x at that point. So this is our first really useful formula with delta functions. If we integrate, it doesn't really matter what we integrate over, minus infinity to infinity will work. Delta of x times any function f of x integrating dx, we just get f of 0. We don't have to do the integral. Delta functions effectively make integrals go away. We can do this not just for the delta function of x, we can do it for delta functions of x minus anything, for instance, x minus a. If we plotted this distribution, delta of x minus a, it's going to be 0, except for the point where x equals a. So at x equals a, the argument is delta function goes to 0. So effectively, we've just translated our delta function over by some distance a. It's not the most clear notation. This is the x-axis and this is a. So what this is going to do, and you can think about doing a change of variables, some sort of u substitution where u equals x minus a, it's just going to give you the value of f at the point where the delta function has support. So this is going to give us f of a. So if we have some way of expressing the delta function, or if we're just using the delta function itself translated, we can pull out the value of f at any point. We can do more with this, though. Instead of just subtracting values in the delta function, we can evaluate the delta function of a function. Again, what we're working with here is integrals multiplied by some other function, since that's how delta functions most often appear in this context. So, if I have coordinates, and what I'm interested in now is g of x plotted as a function of x, Suppose g of x looks something like this. I have some places where g of x crosses the x-axis, where g of x equals 0. I know the delta function is going to be 0 for any argument that's non-zero. So essentially what this is going to do is home in on these regions where g of x is equal to 0. And I drew 5 of them here. Doesn't really matter how many there are. As we consider a broader variety of potentials when we solve the time-independent Schrodinger equation, we get a broader variety of solutions. The potentials that we're considering next have a couple of unique conceptual features that I'd like to talk about in a little more detail. Essentially, when you're trying to solve the time-independent Schrodinger equation for a complicated potential, for instance, a potential v of x that's defined as a function of one region and then another region having a separate function, you may end up with a well-defined solution in region 1 and a well-defined solution in region 2. For instance, if we had, say, a psi of x that was wave-like in region 1 and behaved differently in region 2, for instance, just smoothly curving down to join with the axis, it's useful to be able to combine these two solutions. And the question then is, how do they match up at the boundary? This is the question of boundary conditions, which is the subject of this lecture. The boundary conditions that you need to match two solutions of the Schrodinger equation, the time-independent Schrodinger equation now, can be determined more or less from consideration of the time-independent Schrodinger equation. What is the allowed behavior of a solution? We've discussed the time-independent Schrodinger equation in detail. You know now that this is the kinetic energy operator, and this is in some sense the potential energy operator. But let's focus on the kinetic energy operator, since it has this second derivative of psi. That's where we're going to get a good notion for what's allowed of psi and what's not allowed of psi. Suppose we had a step discontinuity. Is that allowed? What our psi would look like under those circumstances is something like this. Maybe we have a psi that comes in on one side and goes out on the other. If this happens in an infinitely narrow region, we say psi is step discontinuous here. If we wanted to look at, for instance, the kinetic energy associated with a step discontinuity like this, we're going to need to take a second derivative of psi. So if I take the first derivative of psi, the first derivative of a step function is a delta function. If it's not obvious why that's the case, think about what you would get if you integrated from one side of the delta function to the other side of the delta function. If you integrate from, say, a point here to a point here, you'll get 0. If you integrate from a point here to a point here, you'll get 1. Or you'll get some multiple of 1, depending on if you're, say, multiplying by a delta function, like 3 times a delta function or 5 times a delta function. You get 3 or you get 5. So as a function of integrating from this point to this point, you would get 0, 0, 0, 0, 0, some constant, and then increasing your upper limit on your integration doesn't change your final answer. So integrating a delta function from some point on one side of the delta to some variable point gets you a step. And that's more or less, if you go back to the fundamental theorem of calculus, what you expect if you say integrate the derivative as a function of the upper limit of the integral. So the first derivative of our wave function psi here gives us a delta function. If I take then a further derivative, the second derivative with respect to x of my wave function psi, what I'm going to get is going to be the derivative of the delta function. It's going to be 0 away from. Over the past few lectures, we've developed the machinery necessary to solve the time-independent Schrodinger equation with a potential given by a delta function. We've talked about bound and scattering states, and the delta function potential will actually have both solutions, or both types of solution, And we've talked about boundary conditions, which will help us match solutions in the areas away from the delta function, where we can easily express the solutions, we'll be able to make those solutions match at the delta function itself. So, what we're working with is a delta function potential, v of x, and v of x under these circumstances looks something like this. It's 0 everywhere except at a specific point. So we're looking now at v of x as a function of x. It's 0 everywhere except at the origin here, x equals 0. And there, it goes to negative infinity. I'm defining v of x to be minus a times delta of x because we don't necessarily know exactly what the strength of this delta function potential is. You can have different strengths of delta function. If you treat a delta function as a distribution, of course, it has to be normalized. But in this case, we're treating it as a representation of a potential. So we need some constant here which determines the strength of the potential relative to sort of a unit normalized potential. What our solutions will look like under these circumstances depend on the energy of the solution. For instance, if we have an energy up here, E greater than 0, we know we have, in these regions away from x equals 0, we know we have sort of traveling wave solutions. We don't know exactly what happens at x equals 0 here, but we know these are going to look like solutions to our free particle potential, which we discussed a few lectures ago. On the other hand, if we have an energy below 0, then we know what the solutions have to look like. When our energy is below our potential, our solutions have to curve away from the axis. And if we're going to have something normalizable, we need to have the solutions eventually, as they curve away from the axis, instead of curving up to infinity or curving down to minus infinity, they have to just sort of smoothly join in with the axis itself. And we have to have that on both sides of the boundary. But we still don't know what exactly happens at the boundary. That's where our boundary condition matching comes in. But first of all, let's consider what the solution looks like away from the boundary. And in this lecture, I'm going to focus on the bound state, the state where the energy of the state is less than 0. For the bound states, energy less than 0, if what we're looking at is away from x equals 0, then we know v of x is equal to 0. So our time-independent Schrodinger equation becomes minus h bar squared over 2m times the second derivative of psi with respect to x is going to be equal to E times psi. We know the energy now is negative, so we're going to have a negative quantity on the left and a negative quantity on the right. In order to consolidate some constants, let's consider moving the 2m over h bar squared over to the right-hand side here by multiplying through 2m over h bar squared. We'll end up then with d squared dx squared of psi is equal to k squared psi, where I'm defining k to be equal to something that looks a little strange, square root of minus 2me all over h bar. To make the signs clear here, energy is negative, so what we're actually looking at here is the square root of a positive number. We've got a negative energy, positive mass, and negative from the minus sign, negative from the energy. So we're taking the square root of a negative quantity here, so our k constant here is going to be real. Looking at our equation here, you can look at this and think second derivative is giving me something squared times my wave function back. Well, I know what the solution to that sort of differential equation is. It's psi of x is equal to a e to the minus kx plus b e to the kx. This is our general solution, and as is typical in quantum mechanics, if what we're going to have is normalizable, then we can set some conditions on this. our actual space looks like this. We have, as a function of x, our potential is blowing up at x equals 0. So we know we have a solution away from x equals 0. That's what we're trying to find here. If we want a solution on the right here for x greater than 0, and we want our wave function to be normalizable, we know we have to have b equals to 0. Because if we have a non-zero b, integrating, say, the squared modulus of the wave function from 0 to infinity will give us infinity, because we have something growing exponentially here. So for x greater than 0, we know b must be equal to 0. Similarly, for x less than 0, we have to have a equal to 0, because otherwise we have something growing exponentially as x goes to minus infinity. What our overall solution then will look like is in region 1 here, let's say psi 1 of x is going to be equal to a times e to the minus k, or to the e to the kx, whereas in region 2, we're going to have our solution psi 2 is equal to b e to the kx with the minus sign. So e to the minus kx over here, e to the kx over here. What our solution then is going to look like overall is something like this and something like this. And we still don't know exactly what happens at the boundary. So let's figure out what actually happens at the boundary. Our boundary conditions, and we had two of them, was first of all that psi was continuous, and second of all that the first derivative of psi was continuous unless the potential went to infinity. Let's consider the first of those boundary conditions here. Psi continuous. In order to have psi continuous, what this means is that in our regions here we have psi 1 on the left and psi 2 on the right of x equals 0 here. If we're going to match these two conditions continuously, we have to have psi 1 of x equals 0 equal to psi 2 of x equals 0. If I evaluate my solution on the left at the boundary and my solution on the right at the boundary, I have to get continuity, I have to get equality. So if we go back to our general solution, we had our psi 1 was, flipping back a slide a moment to get my a's and b's straight, our psi 1 was a times an exponential growing with x, and psi 2 was b times an exponential decaying with x. So going forwards a slide, our solution in region 1 is a e to the kx. If I'm evaluating that at x equals 0, I have to get something that's equal to b times e to the minus kx evaluated at x equals 0. Now when I evaluate the exponential parts here at x equals 0, I'm substituting in 0 in the exponent. Anything to the 0 is 0, or sorry, is 1. So both of these terms become 1, and I'm just left with a equals b. That helps a lot, but it doesn't tell us everything. Our second boundary condition was that the first derivative of the wave function, d psi dx, was continuous. But it's actually not continuous in this case. We had a condition on this boundary condition. We can only apply this boundary condition when the potential remains finite. And in this case, we have delta function potential at the origin. So we're going to actually break this boundary condition in this case. We're not going to break it beyond all hope of recovery, though. The question is, what does d psi dx do at the boundary? The way to solve this problem is to go back to the Schrodinger equation, the time-independent Schrodinger equation, and keep in mind that our potential now is delta of x. It's a delta function. We actually had a minus sign and an a in front of that. So if we go back and think about what happens with delta functions. Delta functions are only really meaningful when you treat them as distributions and integrate. The trick here, then, is to think about integrating the Schrodinger equation. Where does it make sense to integrate the Schrodinger equation? Well, I don't know anything about the solution. Well, I know everything about the solution away from the boundary, but I don't know what happens at the boundary. So let's just integrate over the boundary. Let's integrate from, say, minus epsilon to epsilon, just integrating over the boundary. To rewrite that, what we've got is minus h bar squared over 2m times the integral from minus epsilon to epsilon of second derivative of psi with respect to x squared. That's our first term. Then substituting in for our delta function, we have minus a integral from minus epsilon to epsilon of delta of x psi of x. And then on the right-hand side, we have an integral from minus epsilon to epsilon of energy, which is a constant and can come out, psi of x. All of these integrals, and I've left them off all over the place, are taken with respect to x. So we have three separate integrals here, and we can figure out what each of these terms look like. Our left-hand term, we have the integral with respect to x of a second derivative. So that's easy. We're just going to get the first derivative. Minus h bar squared over 2m times d psi dx evaluated at the endpoints, epsilon and minus epsilon. So far so good. The second term here, we have minus a, and now we just have a delta function in an integral. Delta functions just pull out the value of whatever else is in the integral wherever the delta function, or wherever the argument of the delta function goes to 0. In this case, delta of x is going to pull out the x equals 0 value of psi. So this is just going to give me psi of 0. On the right-hand side here, I'm going to get something. But the key point about this integral is that we're only integrating over the boundary. We're going from minus epsilon to epsilon. You can probably see where I'm going with this. I'm going to let epsilon be a very small number. As minus epsilon goes to epsilon, or as epsilon goes to 0, I'm essentially integrating this function psi from 0 to 0. So I'm not going to get anything meaningful here. I'm just going to get 0. So this is actually all right. What we've gotten from consideration of integrating the time-independent Schrodinger equation over the boundary with the delta function potential is a condition that tells us how much our first derivative changes at the boundary. If I rearrange this expression here, I'm getting derivative of psi with respect to x evaluated at epsilon minus what I get if I evaluate it at minus epsilon. That's just equal to, rearranging my constants, what is it going to equal to? Minus to 2ma over h bar squared times psi of 0. So that's actually pretty nice to work with. Let me try and move this over a little bit to give myself more space to work. And what we're left with then is substituting our general expression for our solutions for psi, now away from the boundary, into this expression. So we had d psi dx, evaluating this at positive values of epsilon, means I'm in region 2, I'm on the right, which means I'm working with psi 2, evaluating that at x equals 0 on the boundary, subtracting d psi 1 dx, evaluated at x equals 0. So now I'm letting epsilon go to 0, and I'm looking at just the values of the first derivatives. This is our left-hand side over here. We can substitute in values for that because we know what these expressions are, and furthermore, we know that a is equal to b in our expressions for the general solution. So if you refer back to our definitions earlier, what you get here, you're taking the derivative of an exponential, which brings down the k, and we get minus bk e to the minus kx, and we're evaluating this e to the minus kx at x equals 0. So this e to the minus kx is just going to go to 1. So I'm not going to bother writing it. I just get minus bk for the first derivative of psi in region 2 at the boundary. For the first derivative of psi in region 1 at the boundary, now I'm subtracting it because this is the second endpoint, I get a very similar expression. Again, bk e to the now plus kx. And again, evaluating this at 0 means my e to the kx is just going to be 1. The right-hand side now, we had constants minus 2ma over h bar squared, and then the value of psi 0 psi at 0, is just going to be b e to the plus or minus kx. Again, substituting in x equals 0. It doesn't matter if I'm considering the plus or the minus, region 1 or region 2. This is still going to be just 1. So far so good. I can cancel out all of my b's. And what I'm left with, when I simplify a little bit, is minus 2k being equal to minus 2ma over h bar squared. This is the sort of condition we got when we were looking at how the boundary conditions affected the solution to the particle in a box potential, the infinite square well potential. When we actually looked at what the boundary conditions required, and in the case of the particle in a box, it was that the wave function went to 0 at the endpoints of the box, we got quantization. We have quantization again here, except we have a strict equality. There are really no more unknowns in this expression. If you manipulate this further, k equals ma over h bar squared, keeping in mind that k is equal to the square root of minus 2me, where e is a negative number, over h bar, you can solve for the energy. And what you get is that energy is equal to minus ma squared over 2 h bar squared. We have quantized energies. What our wave function then looks like, so far, what we know is that psi of x is equal to, on the left, e, and now substituting back in the definition for k, e to the ma x over h bar squared, if x is less than 0, and e minus ma x over h bar squared, if x is greater than 0. Now, all of this had a b multiplying it out front, which I canceled out here. So my first derivative boundary condition did not help me find b. But there's one more fact that we know about wave functions like this, and that is that the wave function has to be normalized. So if you want to normalize this, you calculate the normalization integral, which you all should know by now. Integral of psi star psi dx has to be equal to 1. You can substitute in this definition for psi, set it equal to 1, do the integral, and find out what b is. This was one of our activities on day 4, so refer back to day 4 if you want to see a little bit about how to normalize a wave function like this. To summarize our results, this is what our normalized bound state solution actually looks like. What you find for the normalization constant is the square root of ma over h bar out front. And now instead of writing it as a piecewise function for positive and negative x, I'm expressing this as an absolute value of x in the exponent. The energy associated with this was minus ma squared over 2h bar squared. We are quantized, but we only have one bound state solution, singular, and this is what it looks like. For a delta function potential, you get these two exponentials decaying as x moves away from the origin. To check your understanding, consider the following two questions. Why is there only a single bound state? And can any initial condition be expressed as a superposition of bound state solutions in this case? We've developed the machinery to solve the time-independent Schrodinger equation for the delta function potential by connecting solutions covering the regions away from the delta function and matching them together with boundary conditions at the delta function itself. The last lecture discussed the bound state solution. This lecture discusses the scattering state solutions. To put this in context, what we're talking about is a potential v of x given in terms of a Dirac delta function. A now is just a constant that defines how strong the delta function actually is. So our potential is everywhere 0, except at some point where it goes to negative infinity. This is a plot now of v of x as a function of x. What we discussed in the last lecture was the bound state solution. What happens if we have an energy E of our state that's less than the potential, less than 0, less than the potential away from the delta function? And what we got was a wave function, psi of x, that looked something like this. Going down towards 0, away from the actual position of the delta function. haven't done a very good job drawing this, but I think you get the idea. The scattering state solutions, by contrast, have energy greater than 0. So we're talking about solutions with energy E up here. At regions away from the delta function, we have basically the behavior of a free particle. We get traveling waves at regions away from the delta function, away from x equals 0. We don't really know what happens at the origin, but we know what our solutions should look like, and we should be able to use our boundary condition matching to figure out what happens at the origin. So what do our scattering states look like? Well, away from x equals 0, we have v of x is equal to 0. That means our Schrodinger equation, the time-independent Schrodinger equation, looks like minus h bar squared over 2m times the second derivative of psi with respect to x. No potential now is just equal to E times psi, where energy now is strictly greater than 0. We can manipulate our constants, much how we did when we were talking about the bound state, and express this as d squared psi dx squared equals minus k squared psi. Now I'm defining a slightly different k than when I was talking about the bound state solution because we have a different sign for the energy. Instead of having k be a negative or imaginary now, I'm going to again have k be positive and real by saying k is equal to the square root of 2me over h bar. If you recall when I was talking about the bound state, I had e less than 0 and I had a minus sign inside this expression. Looking at this ordinary differential equation, we can write down the solution. And the solution is, let's say psi is equal to a e to the I kx plus b e to the minus I kx. When we take the second derivative of this exponential, we'll bring down an ik quantity squared, which will give us a minus k squared. Since we're talking only about regions away from the delta function, we really actually have two general solutions here. We have psi 1 for regions for, say, x less than 0, and we have psi 2 for x greater than 0. Psi 2 now, to the right of the delta function, is going to look very similar, and it's going to be f e to the ikx plus g e to the minus ikx. I should write this as a capital G, sorry. Instead of saying C and D, I've jumped ahead to F and G to eliminate any possible ambiguity if we have to assign future constants, for example, E. So, we have our two general solutions covering regions for negative x and for positive x. What happens at the boundary? How do we match these solutions up? Our boundary condition matching, in terms of these two general solutions, is a two-stage process. We have two distinct boundary conditions, and the first is that psi is continuous. What that means is that psi 1 of 0, our solution for negative x, evaluated at the boundary at x equals 0, must be equal to psi 2 of 0, our solution for positive x's evaluated at the boundary. If I substitute 0 in for these exponentials, for x in these exponentials, what I end up with here is reasonably straightforward. A plus b equals f plus g. That's the result of our continuity boundary condition. And it helps, but it doesn't help all that much. We only get a single equation out of this, so we need to do more. The first derivative boundary condition is that the first derivative of psi is continuous, provided that the potential is finite. However, in this case, our potential is given by delta of x, which does not remain finite at x equals 0. The trick that we used when we were discussing the bound state solution was to effectively integrate the Schrodinger equation dx from one side of the boundary, minus epsilon, to the other side of the boundary, plus epsilon. When we integrate this, we should still have an equality, integrating the terms on the left-hand side and integrating the terms on the right-hand side. And knowing the properties of the delta function, we can simplify this integral greatly. I refer you back to the notes for the last lecture to see what this actually works out to be. What it tells you is that d psi dx, the first derivative of psi, which we get from integrating the second derivative of psi, evaluated at epsilon, and then subtracting the value evaluated at minus epsilon, essentially the change in the first derivative as we go from one side of the boundary to the other, is equal to minus 2 times m times a, the strength of our potential, over h bar squared, times psi evaluated at 0. The right-hand side here we actually got from the integral of our delta function times psi. So this is our boundary condition here, appropriate for use with delta function potentials. This tells us about the behavior of the first derivative of psi as we cross the boundary. So we're going to need to know what our first derivatives actually are. Well, psi1 was equal to a e to the I kx plus b e to the minus I kx. So if I take the first derivative of this and evaluate it at effectively 0, some very small quantity, what I'm going to get for d psi1 dx evaluated at 0, essentially, plus or minus epsilon. I'm looking at psi1 now, so I'm talking about the negative half plane, negative x's. What I get is ik is going to come down from both of these, and I'm going to get an a minus b. I can do the same sort of thing for psi2, which was equal to f e to the I kx plus g e to the minus I kx. When I take the first derivative of this, d psi2 dx, and evaluate it at the boundary, I'll end up with ik times f minus g, by similar reasoning. That means the left-hand side here, which I can calculate by looking at the derivative of psi for positive values of x as x goes to 0, this expression, and subtracting the first derivative of psi for negative values of x as x goes to 0, this expression, what I end up with is ik times f minus g minus ik times a minus b. That's the left-hand side now of our expression up here. Our right-hand side is minus 2ma over h bar squared times the value of psi at x equals 0. Now, if you look at either one of these definitions, you can see what happens when we substitute in x equals 0. We get a plus b for this one, or f plus g for this one, and I have a bit of a choice as to which one I want to use. In this case, I'm going to use a plus b, and you'll see why in a moment. What we end up with now, if you manipulate this expression a little bit and define a useful constant, in this case the constant is going to be beta, just to save some writing, beta is defined to be ma over h bar squared k. What we end up with is f minus g is equal to a 1 plus 2I beta minus b 1 minus 2I beta. And this is the result of our first derivative boundary condition. There's effectively no restriction on these solutions so far. We have something similar to what we had for the free particle. There were no boundaries that were terribly restrictive. We did not end up with a quantization condition. We did not end up with enough of a restriction on our solutions that we ended up with something straight normalizable. But we have our two equations now involving a, b, f, and g. That, unfortunately, is two equations to go with four unknowns. We have our definitions of psi in terms of a, b, f, and g, and these e to the I kx, e to the I minus kx, e to the minus I kx. And then we have our two equations relating a and b and f and g. It seems like we're not going to be able to come up with a very rigorous solution here. But we can actually do a little better if we start thinking about what the initial conditions might actually be. First of all, note that these solutions are the spatial part, and if we add a temporal part to come up with an overall solution for an overall wave function, we'll end up with the same sort of traveling wave states that we had for the free particle. The time dependence for those states was essentially e to the minus I e t over h bar. If you look at each of these terms, you can see this is a plus ikx going with a minus iet. As time increases, space must increase here in order to maintain a constant phase. So, as in our discussion of traveling waves, the plus ikx here for positive values of k is associated with the wave propagating to the right. So if you think about our boundary here at x equals 0, in the space to the left of the boundary, where we're considering psi 1, we have a wave coming in from the left, whose amplitude is given by a. Conversely, the term with b in it here is associated with e to the minus ikx. That represents a wave traveling away from our boundary with amplitude b. The bound states for the finite square well potential are discussed in another lecture. The subject of this lecture is the scattering states for the finite square well, which can be derived in a very similar way. The overall context is our finite square well potential, a potential v of x that's defined to be 0 for x less than minus a, 0 for x greater than a, and a constant minus v naught for x is in between minus a and a. So this is an even potential, and we exploited that fact when we were discussing the bound states where the energy is negative, to figure out what those states look like. And the lowest energy bound state that we found ended up looking something like this. Smoothly joining the axis as x becomes large and negative, smoothly joining the axis for x becomes large and positive, and a smooth curve in between minus a and a inside the well. We found this by examining the general solution for regions less than minus a, between minus a, and greater than a, and smoothly matching those piecewise defined solutions together with the boundary conditions for the Schrodinger equation. We're going to take a very similar approach here, except instead this time we seek scattering state solutions, where the energy E is everywhere above the potential, and as a result our solution can extend all the way from minus infinity to plus infinity. The solutions that we get will end up looking a little something like this, but we'll see what they look like momentarily. Given this potential, we're looking at 3 distinct regions, and we're trying to solve our Schrodinger equation over those regions. Our Schrodinger equation, as always, is minus h bar squared over 2m, second derivative of psi, with respect to x, plus v of x psi is equal to e times psi. Now we know away from our discontinuities, the v of x is going to be a constant, so we expect the overall properties of this solution to be relatively straightforward. And indeed they are. Our 3 regions are divided by x equals minus a and x equals a. For x is less than minus a, our potential here is going to be defined to be 0, and our Schrodinger equation then simplifies to something of the form second partial derivative of psi with respect to x is equal to minus k squared psi, where k is defined as, for instance, in the case of the free particle, as 2me over h bar squared, k squared is 2me over h bar squared. We know the solution to this case for the free particle gave us traveling waves, and we're going to reuse that form of our solution here. We'll have psi being equal to a e to the ikx plus b e to the minus ikx. Traveling waves moving to the right and traveling waves moving to the left. Of course, nothing is traveling about this now, since we're just looking at solutions to the time-independent Schrodinger equation. But if you, as before, add the time dependence to these solutions, you find that they are indeed traveling waves. That was for the region where x is less than minus a. The region where x is greater than minus a is going to give us something very similar. It's going to give us an exactly identical Schrodinger equation, and it's going to give us exactly identical solutions, except we'll be working with slightly different constants. Our wave function psi is going to be given by, in this case I'll call it f e to the ikx plus g e to the minus ikx. Now I've used different constants for f and g, but the same constant for k, since overall we're trying to solve the same Schrodinger equation, so we have effectively the same value for e, and therefore the same value for k, as defined in terms of 2me over h bar squared. For the region in between minus a and plus a, we're going to have a slightly different Schrodinger equation. It's going to give us essentially the same sorts of solution, though, but I'm going to write them slightly differently. Our overall Schrodinger equation will become, as before, the second derivative of psi is equal to minus some constant times psi, but the constant is going to be different. The constant, instead of being 2m e over h bar, is going to be 2m over h bar squared times e minus v. E minus v naught, but since, e minus v of x, let me step this out a little bit, e minus v of x, since v of x in the region between minus a and a is minus v naught, this is effectively e plus v naught. So we have our constants here, and in the case of these solutions, we could easily write them in terms of traveling waves with L instead of K, but it's actually slightly easier here to write them instead in terms of sines and cosines. This is just as general as a solution, but let's write psi in this regime as c times the sine of Lx plus d times the cosine of Lx. Apologies for being messy here. These are then our three general solutions. We can call them psi 1, psi 2, and psi 3, if you like. But these are general solutions to the Schrodinger equation, the time-independent Schrodinger equation, for these three regions. The next step is to mesh these solutions together with our boundary conditions. We had two boundary conditions, and if you're unfamiliar with the boundary conditions that we'll be using under these circumstances, I suggest you go back and examine the lecture on boundary conditions. The first of our boundary conditions was that the wave function is continuous, and the second was that the first derivative of the wave function is continuous. And there are sound physical reasons that that has to be the case. For instance, if the wave function itself is discontinuous, the expectation value for the kinetic energy of the wave function diverges to infinity and cannot be a physical state. But considering the boundary at x equals minus a, ensuring that the boundary condition holds means meshing the value of this wave function at minus a and the value of this wave function at minus a. Excuse me. So let's go ahead and plug that in. Our boundary condition at minus a here is going to give us a e to the minus I kx plus b e to the I kx, oh, sorry, not x, we're plugging in for x, minus I ka, and then b e to the I ka, since I'm substituting in minus a for x. That's what I get for this region. That has to be equal to what I get for this region, which in this case I will write as minus c sine La plus d cosine La. Now if I substitute in minus a for x here, I would actually get the sign of minus La, but since sine is an odd function, I'm pulling the minus sign out front and writing this as minus c times the sine of La, just to keep the arguments inside all of the trig functions consistent. So this is our boundary condition for the continuity of psi. We have another boundary condition for the first derivative of psi, and you can write that down more or less just as easily by noting that in either of these cases, taking the first derivative with respect to x is going to bring down an ik. So we'll end up with ik times the quantity a e to the minus I ka plus b e to the I ka, and I've screwed up the minus signs already. Since the sign here is going to bring down a minus ik, when I factor out the ik, I'll still be left with the minus sign. So that's our first derivative of the wave function in this region. And if we're going to ensure continuity of the first derivative, we must also equal the first derivative of this wave function evaluated at the boundary. Taking the first derivative of sine and of cosine is going to pull out an L, so I'm going to have something that looks similar. I'm going to have L times the quantity, then the derivative of sine is cosine, c cosine La, and the derivative of cosine is minus sine, so I'm going to have minus d sine, and I'm evaluating it at minus La again, which I'm going to use to cancel out this minus sign. Sine of minus an argument is minus the sign of the argument, so I have two minus signs, and I end up with a plus overall. So these are our boundary conditions at x equals minus a. We get very similar expressions for our boundary conditions at plus a, but before I write them down, I'm going to make an additional simplification. Since what we're considering here are scattering states, for instance, in our consideration of the scattering of scattering states off of a delta function potential, we had a wave incident from the left, a wave bouncing back to the left, and we had a wave that was transmitted through. That was for a single potential. If we have some potential well, we're still probably interested in the same sort of process, a wave incident from the left, a wave scattering back to the left, and a wave transmitted through to the right. We're probably not so concerned with the wave coming in from the right, so I'm going to get rid of that one, and that amounts to setting g equal to 0 for our general solution in this regime. So we're no longer working with a fully general solution, but we have one fewer unknown to work with since we've gotten rid of g, which simplifies the algebra quite a lot. Makes it solvable, in fact. So, going through the same procedure we did at minus a, instead evaluating the wave function and its first derivative at a, the expressions we get are c sine LA plus d cosine LA is equal to f e to the I k a. That's from just continuity, plugging in x equals a into this expression and setting it equal to plugging x equals a into this expression. Our first derivative, again, by taking the first derivative and repeating the process, gives you L times c times the cosine of LA minus now d times the sine of LA. We have a minus sign here because now we get the minus sign from taking the derivative of cosine, and we're substituting in plus a, so what I did to get a plus sign here no longer works. I can't factor a minus sign out. That's our left-hand side, and it's going to be equal to, first derivative of this brings down an ik, as before, ik f e to the I k a. So those are our general boundary conditions, and we have essentially 5 equations and 4 unknowns here. We have a, b, c, d, f, and k, all being unknown. K is determined entirely by the energy, and since what we're working with here are scattering states, linear algebra is very useful for quantum mechanics. We've already used a lot of the notation and terminology of linear algebra when we say, for instance, that 2 wave functions are orthogonal to each other. But quantum mechanics puts its own spin on things. In part, for instance, because we're not dealing with, say, 3-dimensional Cartesian coordinates. We're dealing with a complex vector space that describes the state of a physical system. So dealing with complex numbers and dealing with vector spaces in a more general way is very useful, especially as we move away from simply solving the Schrodinger equation, but to manipulating solutions to the Schrodinger equation to infer the properties of physical systems. So linear algebra will be useful in the coming chapters. To justify why this is useful, I'm going to make a couple of analogies. There are some things that we can say on the basis of vectors. We have vectors, A. We can make dot products between 2 vectors. We can express a vector A in, say, Cartesian coordinates, ax x hat plus ay y hat plus az z hat. We can also express some vector A in a different coordinate system. I'll call it a sub alpha, not x hat, excuse me, alpha hat plus a beta hat plus a gamma hat, where now the hatted vectors here are unit vectors, and the numbers ax, ay, az, a alpha, a beta, and a gamma are simply coordinates, or simply components. They're simply numbers. If these x, y, and z, alpha, beta, and gamma represent different coordinate systems, we can still say that this is the same geometrical object, A. The vector A is not changed by expressing it in different coordinate systems. It exists independent of any coordinate system. And of course, we can also take dot products of unit vectors with themselves and get 1. Quantum mechanically speaking, each of these expressions in terms of vectors has an analog. The vector A That's what we've been talking about so far as, say, psi of x. That's the state of the physical system, the wave function. Taking the dot product of two vectors, that's our integral from minus infinity of, say, psi sub a star of x times psi sub b star of x integral dx. Expressing a vector in terms of one coordinate system versus in terms of another coordinate system is essentially the difference between looking at the state of the system as the wave function psi of x versus the wave function in momentum space, the wave function phi of k, which we got by taking Fourier transforms back when we considered the free particle. Our whirlwind tour of linear algebra continues with linear transformations. Here, we'll write linear transformations with hats. For instance, t with a hat, capital letters especially, will be considered to be transformations. A linear transformation, quite simply, is a transformation that's linear. What it means for something to be linear is if I apply the transformation to a times the vector alpha plus b times the vector beta, I get a times the transformation t applied to the vector alpha plus b times t applied to the vector beta. If this sort of identity holds, the transformation you're working with is linear. It's difficult to work with transformations in general, so it's useful to consider what a transformation looks like if we have a vector in a particular basis. So suppose I have a set of basis vectors, x sub I. I'm not telling you how big this set of basis vectors is, but if we have our transformation applied to the basis vector x sub I, let's say x sub 1 in particular, that transformation applied to a basis vector will be given by another vector, which is in general going to be expressed as a sum of basis vectors. So x1 will be transformed into some number, which I'll write as t11 x1, vector x1, not xi, excuse me, tx1, plus some other number, t21 times the vector x2, plus t31 times the vector x3, etc., up to xn. If I have, say, x2, I get a similar expression, except I'm going to number things slightly differently. I'll say this is the t12 number, is the x1 component of the transformation applied to x2, plus, etc., t22 x2 plus t32 x3 plus, etc. So if I have some vector then, alpha, being expressed as a1 x1 plus a2 x2 plus a3. The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function, let's say psi of x and t. And to some extent, you can write down sort of closed form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian or a sinusoid or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrodinger equation. We're talking about, say, particle in a box or the quantum harmonic oscillator. It gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity. Instead of summing, we're computing an integral. We're integrating perhaps decay, if we're working with the free particle, for instance. And we have some sort of a phi of k, some sort of a coefficient that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t. And there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed-form mathematical function, some sort of a list of coefficients, some sort of a function, there's actually more going on behind the scenes. We also have this notion of operators relating different states to each other, and these expressions are going to be true regardless of the nature of psi 1 or psi n and psi n minus 1. That expression has to hold. Why? Well, there is a deep mathematical structure going on behind the scenes here. So let's explore that mathematical structure. That's what this chapter is all about. So, what we're working with here, like I said at the beginning, technically speaking, is linear algebra in Hilbert space. Now, if you've studied linear algebra, you know it deals a lot with vectors, and you can gain a lot of intuition about the behavior of physical systems in terms of vectors. So, say we have some sort of a vector A pointing in that direction, some sort of a vector B pointing in that direction. You can do basic vector operations on these things. We can, for instance, take the dot product of A and B. And I've drawn these things as approximately perpendicular to each other, so you would expect the dot product to maybe be 0. We can also write perhaps the vector B as some sort of linear transformation acting on a vector A. And in the language of three-dimensional vectors, it's easy to write down linear transformations as matrices, in this case 3 by 3 matrices. So if you've studied linear algebra, these sorts of concepts are familiar to you. In particular, there are a lot of linear algebra concepts, things like the inner product or normalization or orthogonality and the notion of a basis that we can express. Now, the nuance in quantum mechanics is that we're working with a Hilbert space. And a Hilbert space, technically speaking, is an infinite dimensional vector space. So the infinite dimensionality here, I think I've actually written infinite, but you get the idea. Instead of working in 3 dimensions, we're working in infinite dimensions. Instead of lists of 3 numbers, we need lists of infinitely many numbers. And that makes life a little bit more difficult. The basic structure ends up being the same, though, so much of your linear algebra experience is still going to hold here. To give you some basic vocabulary and basic intuition, we're dealing with vectors, first of all. And the notation that we'll use for a vector in the notion of a vector in this Hilbert space is going to be something like this. So, vertical bar, name of vector, and then angle bracket. We'll expand on this notation much more later on in the chapter, but for now, just think of this vector as somehow representing the state of the system. As a proxy, think something like psi of x, if you need a more concrete representation of the state. You don't want to just think in general. Now, I contend that when we're talking about linear algebra and Hilbert space as applied to quantum mechanics, this representation is actually more useful than the wave function. And we'll see why that's the case later on. Oftentimes, we don't need to know anything about the wave function to still make useful conclusions on the basis of the vectors themselves. So what else can we do in terms of linear algebra? Well, we can do inner products. The way we'll write that in this notation is BA, or beta alpha here, angle bracket, beta, vertical bar, alpha, angle bracket. In the language of states and wave functions, you can represent inner products like this as integrals, minus infinity to infinity, of, in this case, let's say, psi beta star as a function of x times psi alpha of x, all integrated to dx. This is that same sort of normalization and orthogonality integral that we've been dealing with a lot in the context of wave functions, but expressed in a more compact notation, in a more general mathematical form, that of linear algebra. With this notion for an inner product, we can also think about normalization. Something like the vector alpha inner product with the vector alpha would translate into wave function language as an integral from minus infinity to infinity of psi sub alpha of x, psi sub alpha of x, need to complex conjugate this one, sorry about that, dx.
And in terms of normalization, this had better equal 1, and this had better equal 1. So the inner product of a vector in this Hilbert space with itself had better give you 1 if this is going to represent a valid quantum mechanical state, same as the wave function has to integrate in the squared modulus context to give you 1. We can also talk about orthogonality. Orthogonality, in the language of linear algebra, refers to the vectors being perpendicular to each other if you're just thinking in 3 dimensions. Now, in infinite dimensions, it's a little bit harder to express, a little bit harder to think about, but it's just as easy to write down. I can say alpha and beta equals 0. That means these vectors are orthogonal to each other. In the language of integrals here, integral from minus infinity to infinity of psi alpha of x, complex conjugate, psi beta of x, is going to give you 0. If these come from, for instance, a solution to the time-independent Schrodinger equation, perhaps we have a set of wave functions to work with. I'll write that as a set of states, say psi sub n. I may be guaranteed that psi sub n inner product with psi sub m gives me a Kronecker delta. This would express orthonormality, that this set is every element in this set is orthogonal with every other element, and that each element of the set is properly normalized. We can also talk about the completeness of a basis. So working with this sort of set psi n, suppose it comes from solving the Schrodinger equation in the language of the wave function, I can express some arbitrary psi, arbitrary quantum mechanical state, as a sum of, let's say, n equals 1 to infinity potentially, of a sub n psi sub n. If this sort of expression is possible, these psi sub n's form a complete basis. And if you think about invoking the orthogonality and applying Fourier's trick to this sort of expression, that works out just as well. You can figure out that in this case, a sub n is going to be what you get if you take the inner product of psi sub n with this arbitrary wave function that we're starting with. Now, these expressions have corresponding versions in terms of the wave function as well, but since I'm running out of space on the slide, I'm not going to go into the details. This one is going to be an inner product, same sort of integral as we're working with here. Likewise, this is your infinite sum. I think I had that expression on the last slide. Now, within the language of linear algebra and Hilbert space, we have this sort of notation, these sorts of representations for what these states really are as they exist in the vector space, or in the Hilbert space. What can we do with these states? Well, the fundamental question in quantum mechanics generally has to do with the observable properties of a system. So what do we have in the language of observables? Well, observables we know are going to be real numbers, and they have some sort of statistical properties in quantum mechanics. For instance, we talked about the expectation value. Say I have some sort of observable Q, I can write the expectation value as Q inside a pair of angle brackets. And the angle brackets here are not exactly the same as the angle brackets in the earlier expressions that we've been working with, but there is a connection. We'll come back to that later. If you want to think about the expectation value, for example, in terms of some sort of quantum mechanical system, we're dealing with an operator. So the observable isn't just going to be the expectation value of some Q, some quantity Q. We've got some sort of an operator, which I'll write as capital Q with a hat. So what would our expectation value Q look like in this language of angle brackets? Well, we know what it looks like in terms of inner products, or in terms of integrals of wave functions, for example. It's going to be an integral of the wave function, the state of the system, then the operator, then the wave function of the state of the system. And we have that same sort of notation in context of inner products in our vector space. So we would have the state of our system, psi, and we have our operator acting on psi. So the operator acting on psi gives you, in some sense, another state of the system. It's not really another state of the system, though. It's more a vector in this Hilbert space. Operators here, if I think about this Q operator acting on the state of the system, is going to give you some new vector in your Hilbert space. Now, we know that this sort of expectation value quantity or concept has to result in some sort of a real number. So you can think about this as, what happens if I take the complex conjugate of this? Well, if you're thinking about psi, q hat psi, complex conjugated, in the language of the integrals that we've been working with, this is going to be taking the complex conjugate of q hat psi. So instead of being a psi star q hat psi, it's going to be a q hat psi star multiplied by psi inside the integral. And the same notation sort of holds here. Whenever you take the complex conjugate of an inner product like this in our Hilbert space, you swap the order of these things. Instead of the psi being on the left, the psi is on the right. And the q hat psi on the right is on the left. So this notion of what appears on the left and what appears on the right is a useful way of keeping track of what's been complex conjugated. So q hat psi psi in our revised notation here. Now this sort of substitution here, if this is going to be equal to the original expectation value of q, right? Complex conjugate of the expectation value has to be equal to the expectation value itself if this is going to be a real number. This expression has to be equal to this expression. And the equality of two operator expressions in the language of linear algebra like this, essentially the operator can act on the left or the operator can act on the right. The operator behaves the same when acting on a complex conjugate of the state as it does on the state itself. Complex conjugate of state with operator gives you the same result. That is only going to be true if the operator here is Hermitian. And there's lots more that can be said about the notion of Hermitian operators, and we'll come back to that in further lectures. But for now, know that there's a lot of mathematical formalism that goes along with linear transformations, such as vectors to new vectors in the space, especially associated with Hermitian linear transformations. So as an example of the notion of a Hermitian operator and how that manifests itself in this context, think about the momentum operator. Is the momentum operator Hermitian? Well, if the momentum operator is Hermitian, we know that if I have some sort of a wave function f, the momentum operator acting on the wave function g has to be equal to the momentum operator acting on f, inner product with the wave function g. Sorry, I shouldn't say wave function, I should say state. State f, momentum operator g, momentum operator f, state g. These things should be equal to each other. So let's do some manipulations of the one on the left. And just since we have a large amount of machinery for working with the notion of states in terms of wave functions, let's express this in terms of wave functions. So our inner product in terms of the wave functions is going to be the integral from minus infinity to infinity of some wave function f, complex conjugated, as a function of x, multiplied by the momentum operator applied to our wave function g. And our momentum operator is minus I h bar, partial derivative, with respect to x. So this is acting on the function g of x, and we're integrating dx. Now this is an expression that looks a little bit difficult to work with. We have partial derivatives inside an integral, but whenever you see a derivative inside an integral, think integration by parts. So let's say I do integration by parts. I can define my variable u to be some sort of f complex conjugate, recognizing the parts that I would like to differentiate. And the part that I would like to integrate would be, well, the part that's already been differentiated. So let's say dv is equal to partial g partial x with dx tacked on. So identifying this part as my v and this part as my u. And you can pull the constants out front if you want. So this is going to give me du would be the partial derivative of f star partial x, and my v when I integrate it, now it's the integral of the derivative, so fundamental theorem of calculus just gives me g. Integration by parts then says this whole thing is going to be equal to f star of x, g of x, evaluated at my boundary, minus infinity to infinity, minus the integral from minus infinity to infinity of these two guys, v du. So I have my partial f, partial x, and I have my g, and I'm integrating dx. Technically I should put a dx there in my integration by parts notation. So, as usual in quantum mechanics, we require these functions to be square integrable, meaning normalizable, meaning they have to go to 0 at infinity. So 0 at plus infinity, 0 at minus infinity, this term all by itself drops out. Oh, and I've got this coefficient overall that I should pull out front. So minus I h bar multiplies all of this. So I've got a minus I h bar and a minus. The minus I h bar and the minus are going to cancel out if you want to simplify this, and I'll have I h bar. Let me put that inside the integral. I h bar, I have a partial derivative of f star, partial x, and g, and I'm integrating dx. So we're almost there. This looks a lot like the momentum operator applied to the function f. So we've almost sort of closed the loop here. We've almost shown that p is Hermitian. What's missing here? Well, what's missing is the notion of this minus sign on the I h bar. This here itself is not exactly the momentum operator applied to f. But what we want actually isn't exactly the momentum operator applied to f. It's the momentum operator applied to f, but then acting on the left in this inner product notation, which means we have to take the complex conjugate. So if I really wanted to write this out, I would have to say this is the integral, put some limits on here, minus infinity to infinity of minus I h bar partial f partial x, all complex conjugated, multiplied by g integrated to dx. And now we've actually gotten back to this original expression. This here is the operator p acting on f, complex conjugated, inner product with the function g. So that's the end result. We have sort of demonstrated that our definition of minus I h bar partial g partial x here is indeed a Hermitian operator. And perhaps this goes a little bit of the way towards explaining why exactly you had a minus I h bar, or minus I, in the definition of the momentum operator. That minus I is a little bit perplexing at first, but it is required essentially by the notion that the momentum operator be Hermitian, by the notion that the expectation value of the momentum is always going to be a real number. As a further example of how we can manipulate these sorts of things in the language of formal linear algebra, let's think about a state with no uncertainty. What sort of quantum mechanical state would have no uncertainty? These things are also called determinate states, meaning you have some operator or some observable, let's say the observable q as represented by the operator q hat, and it has absolutely no uncertainty associated with it. There is a quantum mechanical state that has a definite value of some variable, some observable. Now, if you're thinking about something like position or momentum, you might be thinking along the lines of the uncertainty principle, and well, is that really possible? And the answer is probably not. The states of determinate position and determinate momentum tend to be a little bit poorly behaved, mathematically speaking. But in terms of energy, perhaps, you know states of determinate energy. They are the solutions to the time-independent Schrödinger equation. So there's certainly nothing wrong with that. In particular, I can write something like sigma q, the variance, sigma q squared, the uncertainty in a measurement of quantity q squared. And I can write that this quantity was, back when we were talking about variance and probability distributions, defined as the expectation value of the operator q minus the expectation of q. So the deviation of some observable from its mean squared. So the expected mean squared deviation, the mean squared deviation from the expected value. Now, in our language of linear algebra here, we can write this out as psi on the left, and then q hat minus the expected value of q acting on psi on the right. Oh, and this is squared, of course. So I can expand out the square, let's say psi on the left, and then q hat minus expected value of q hat minus expected value of q twice, acting on psi. And this operator, if this is going to represent an observable, has to be Hermitian. So if q hat, the operator, is Hermitian, q, multiplication by a number here, the expected value of q, this is just going to be a number. It's also, of course, going to be Hermitian. Multiplication by a number is going to be a Hermitian operator. It doesn't matter if you do it on the wave function on the right or the wave function on the left. I can take this whole thing and apply it on the left, since this is a Hermitian operator. So if you make that sort of manipulation, you end up with, now on the left, I have q hat minus expectation of q acting on psi, and on the right, q hat minus expectation of q acting on psi. And if this whole thing is going to have zero uncertainty, what exactly does that mean? Well, if this whole inner product is going to turn out to be zero, then either psi equals zero, meaning my wave function is in some sense trivial. That's not terribly useful. If psi is not zero, then each individual piece here, this has to in some sense be equal to zero. Or this piece on the left has to be equal to zero. What that means, well, either left and right, these are very similar expressions. It means q hat minus the expected value of q. In terms of that as an operator acting on my state, that has to equal zero. And that's easily rearranged into q hat acting on the state equals the expected value of q multiplied by the state. This is just a number, it's not an operator. This here, this is an eigenvalue problem. And there is yet another massive set of linear algebra machinery dedicated to solving eigenvalue problems. We've already done some of them. For example, the Hamiltonian operator acting on the state of the system is the energy times the state of the system. This is their time-independent Schrodinger equation. This gave us the states of definite energies, and that's the same sort of framework as you got in here. So that's a taste of the sorts of things that we can represent and think about in the language of linear algebra as applied to quantum mechanics. We can express generalized states with no uncertainty and derive that they are going to be the states that are eigenstates of the linear operators that represent the observables. Now, we haven't really written down any linear operators in detail in the notation of linear algebra or really in quantum mechanics. We've only really got a few operators that we can work with, like Hamiltonian and position and momentum and whatnot. But this is hopefully I have at least convinced you that there's more to quantum mechanics than just dealing with the wave function, that we can do some interesting things with the linear algebra structure. So to check your understanding here, let's consider a set of states that you get, stationary states from the quantum harmonic oscillator. That means the solution to the time-independent Schrodinger equation, which if you wanted to write it out in terms of operators and linear algebra, is h bar psi sub I, let's say psi n actually, is equal to En psi n. So that would give us this set of solutions here. So in terms of the language of linear algebra, some basic notational questions. And in terms of whether or not observable operators are Hermitian or not, think about why the operator x hat, the position operator, would be Hermitian. Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write Q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, F, inner product with the operator acting on some arbitrary state in the Hilbert space, G, is going to be equal to the operator acting on the state F, inner product with the state G. So if this inner product and this inner product are equal to each other for all F and G, then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything. It only changes the overall scaling factor by some amount q. So these sorts of eigenvalue problems show up in quantum mechanics all over the place. For example, the time-independent Schrodinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state. H psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Those are going to be the values of Q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many Q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of Q in this sort of expression. And the sets of psi's and the sets of Q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrodinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that looked something like, well, there was some free parameter k. And our wave function as a function of x looked something like a complex exponential. We had e to the I kx minus h bar k squared over 2m t for the time dependence. Probably we were dividing this by root 2 pi, if I remember correctly, to effectively normalize it within the language of the Fourier transform, at least. So there's no way of writing down psi 1, psi 2, psi 3, psi 4. There is only psi k, and k can take on essentially any value. The eigenvalue that we got was, well, in the case of the momentum operator, h bar k. Given the definition of k that we came up with in this consideration of the free particle, we have an infinite set of continuously variable solutions. This k value can be anything, as opposed to indexed by just an integer 1, 2, or 3 sort of setup. Now, the mathematics that results from a discrete spectrum, a discrete set of eigenvalues, versus a continuous spectrum, a continuous set of eigenvalues, are going to be a little bit different. But it's a little easier to understand the discrete case. It's a lot easier to write down mathematical expressions, so let's consider that case first. Most of the results will still hold, and we'll come back to the continuous case later on in lecture. So, the first thing that you probably want to know about the eigenvalues that result from these eigenvalue problems is whether or not they can possibly represent observables. And in this case, the eigenvalues of Hermitian operators are real. You can see that by fairly straightforward application of the eigenvalue equation itself, looking at q hat, the operator, applied to some arbitrary wave function psi, giving you the eigenvalue q, multiplied by the wave function psi. You can take the complex conjugate of that expression, and complex conjugating the left-hand side merely converts this into, well, the result of complex conjugating the operator acting on the wave, or acting on the state, which we're writing in our vector notation as angle bracket on the left instead of angle bracket on the right. Complex conjugating the right-hand side of this expression gives you, well, the complex conjugate of the eigenvalue, q star, multiplied by the result of complex conjugating this wave function, or this state, psi. So again, angle bracket on the left. The other ingredient to understanding why the eigenvalues of Hermitian operators are real is the definition of a Hermitian operator, which says that q acting on some state f, inner product with the same state f perhaps, is going to give you the same result as if you take the inner product of the state f itself with the operator acting on the state f on the right. Operator on the left, operator on the right gives you the same result. Now, if I apply this sort of expression over here, and this sort of expression over here, you can see what's going to happen. Applying the operator on the left turns this into q complex conjugate F, inner product with F. And applying this expression on the right turns this part into Q, the number, multiplying F. Now a number inside an inner product like this is just going to factor out. So we're left with Q, the number, times F, inner product with F. And the inner product of a state with itself is always going to be non-zero. So I can effectively divide both sides of the equation by this, and thereby show that Q star is equal to Q. Therefore, our eigenvalues of the eigenvalue problem for a Hermitian operator is going to be a real number. Real numbers means that these are potentially feasible representations of observable quantities. So that's a step in the right direction. Now, we talked about a lot of other facets of solutions for the time-independent Schrodinger equation, for example. What about orthogonality and normalization and whatnot? We can talk about those within the language of eigenvectors and eigenvalues, eigenstates of a Hermitian operator. It turns out the eigenstates of a Hermitian operator are orthogonal to each other. Now, that's not a completely rigorous mathematical statement. I'll point out some of the difficulties with it later on. But in the context of orthogonality, we're talking about an inner product of two different states. So suppose I have Q hat, and I'll say the state F gives me some eigenvalue QF, multiplying the state. And then I have a distinct state Q, let's call it G, gives me the eigenvalue, not G, sorry, QG, multiplying the state G. These two eigenvalue problems are solved for the state F and for the state G. So in principle, I know F, I know G, or QF, I know G, I know QG. Now, if you consider the definition of a Hermitian operator in the context of the states F and G, I have F acting on Q times G, and that has to be equal to Q acting on F, inner product with G. This is our definition of a Hermitian operator. And we know, considering eigenvalues and our eigenvalue problems here, QG, I can write down that. That's just going to give me Q sub G times the state G. So this is going to give me QG times the inner product of F and G. And QF on the left, we've talked about how to do that sort of thing on the last slide. This is just the complex conjugate of this sort of thing. So this is going to give me QF, complex conjugated, times the inner product of F and G. Now this looks a lot like the sort of expression we were talking about before, but in the case of showing that the eigenvalues were purely real, we were working with the state F and itself, not the state F and some other state G. So, we have some potential problems with this expression. If QG and QF are not equal to each other, and F and G, the inner product here, is non-zero, then we have the same expression on both sides, can be divided out. QG is equal to QF, but that's going to cause some problems. The problem that we run into is that we have a failure of our inequality here. And the inequality that fails if I say divide these things out, if QG is different than QF, then I have a contradiction. The contradiction is that F and G don't have non-zero inner product. If F and G has zero inner product, I can't just divide it out because I'm dividing both sides of my equation by zero. So what we can conclude from this expression is that either FG is equal to 0 or QG is equal to QF. And I'll just say QG is equal to QF. Since we've just shown that the eigenvalues are real, QF star is equal to QF. So we've shown that if the eigenvalues are different from each other, then the inner product must be 0. If the eigenvalues are the same, we are not guaranteed that the eigenstates, F and G, will be orthogonal to each other. In the case that QF equals QG, we describe the eigenvalue as degenerate, and we have to go through some extra procedures in order to ensure that we have a well-behaved set of eigenstates. In particular, what we want to do is something called Gram-Schmidt orthogonalization. And aside from having a lot of letters in it, orthogonalization is simply the process of taking these two states, F and G, and converting them into two new states, F prime and G prime, that are constructed as superpositions of F and G, such that they are actually orthogonal. I won't go into the details here, but it has to do essentially with finding the component of the vector F that is not orthogonal to the vector G and subtracting it off of the original vector F, so that I only have the part of F that is orthogonal to G left over when I've computed F prime. So that's a little bit about the eigenfunctions in terms of their orthogonality. The other thing that we needed to be able to compute meaningfully in quantum mechanics is completeness. We needed to represent states, arbitrary states, as superpositions of, for instance, stationary states, solutions to the time-independent Schrodinger equation for, say, the quantum harmonic oscillator. In the language of linear algebra, the mathematical formalism of quantum mechanics, that's an eigenvalue problem with the Hamiltonian operator. And it turns out that we have the same sort of mathematical formalism there. The eigenstates of Hermitian operators are indeed complete. And I can't really say much more here than just give you a definition. In terms of the completeness, we're talking about our eigenvalue problem as before, giving us a spectrum of eigenstates, let's say psi sub n, and the resulting set of eigenvalues. And it turns out that this is indeed a complete basis. Within the language of linear algebra, the set of vectors here spans the complete space that you're working with. And what that means is that any arbitrary state, let me call it F, can be written as a superposition. Let's say n equals 1 to infinity here, of some coefficient n multiplying psi n. So I can express any vector in my vector space as a superposition of this set of vectors. It forms a complete basis that spans any desired function that you would be interested in. You can, given the orthogonality of these states, as shown in the last slide, apply Fourier's trick to this sort of expression and determine that this a sub n coefficient is fairly straightforward to calculate. You just multiply from the left by psi sub n, take the inner product with the state that you want to represent. Now, it's important to note that this sort of statement is not on as solid a mathematical footing as the earlier states regarding orthogonality. The completeness is often not easily proven. It is typically going to be something that we assume, and while in the case of consideration of the wave function, we can write down the time-independent Schrodinger equation as a partial differential equation and apply the language of Sturm-Liouville theory and apply the results of Sturm-Liouville theory, in particular to show that the results are complete, or the set of solutions to the time-independent Schrodinger equation forms a complete set of basis functions. The same sorts of results are typically going to apply here. So while we can't always prove it, we are generally going to assume it, certainly at the level of mathematical sophistication of a course like this. So that's about it for the results. One thing I did want to say before we close here is that all of what I've been stating so far are for discrete spectra. So what about continuous spectra? What if, instead of getting a discrete set of eigenstates and eigenvalues, I get a continuous set of eigenstates and eigenvalues? The example I gave earlier was a consideration of the momentum operator as an eigenvalue problem. If I have some arbitrary function, apply the momentum operator, and get that same function back, the solutions that we got looked something like e to the I kx minus h bar k squared over 2mt, with eigenvalues that look like h bar k. Now, first problem, this is not normalizable. So within the language of linear algebra, writing down something like, if I call this psi sub k in the language of linear algebra, writing down something like psi k, what exactly sense does that make? Can I really say this is normalized? Well, if I have two different values of k. Let me say, express this in terms of momentum instead. So I'll write this as a psi sub p. If you consider, say, psi p1 inner product with psi p2, what does the orthogonality actually look like? Orthogonality or normalization? Well, if you write this out in the language that we know, that we've been working with so far, that of wave functions, this is going to be the integral from minus infinity to infinity of, well, this sort of expression. First of all, I've got psi sub p1 complex conjugated, so that's going to be e to the minus I k1x minus h bar k1 squared over 2mt multiplied by e to the plus I k2x minus h bar k2 squared over 2mt. This is all going to be integrated dx from minus infinity to infinity. So in the case that p1 equals p2, meaning this is really the same state, then the exponential argument here is the same, but has opposite sign. So I've got e to the plus something times e to the minus something, which is just going to give me 1. I'm going to get the integral of minus infinity from minus infinity to infinity of 1 dx. What now? That's going to be infinity, surely, right? It's not a very meaningful expression, but it's going to give me something very large. Now, what if, let me move this over a little bit to the left, what if I consider p1 not equal to p2 then? Well, in that case, my integral here is going to have some function of x. k1, k2 are going to be different. In the subtraction here that I get if I combine these two things, I'm going to get some function of x. It's going to be like the integral of minus infinity to infinity of e to the I something x. There's going to be other stuff up here as well. But I've got this sort of oscillatory behavior. You can think of this as cosine plus I sine, in other words. Now, as far as formally defining this mathematically, what this limit says, you've got an oscillatory function, you're integrating it all the way to infinity. It's not going to go to infinity, it's going to oscillate, right? And it's going to oscillate about 0. It's going to average out to 0. So in some sense, we can say this sort of goes to 0. And I should really put this in quotes so that I don't make my inner mathematician too angry. We do know, however, from working with these in the past, that these do form a complete basis. These sorts of things can be used to express any arbitrary initial conditions. We talked about that in the context of the free particle when we wrote expressions like that the wave function psi of x, say, can be written as an integral from minus infinity to infinity of dk some coefficient phi of k multiplied by, say, e to the ikx. These sorts of expressions, this is like the inverse Fourier transform of psi sub k. So given some suitable definition of psi sub k, these e to the ikx, these sorts of functions can actually represent pretty much anything that you might want. Now, if we substitute in our definition for phi of k back from when we were talking about these sorts of things, it looks like this. It's the integral from minus infinity to infinity dk from before, and our phi of k was itself an integral from minus infinity to infinity. This time it was an integral dx, and it was, let's not leave it as an integral dx because I've got x in this expression as well. Let's use a dummy variable, my usual squiggle, xi. Integral dxi of psi of xi e to the minus I k xi. So this sort of expression, that was our definition of phi sub k. If I multiply this by e to the I kx, continuing my expression over here, you end up with something that makes a certain amount of sense. In particular, I can manipulate this. Let's consider exchanging the order of integration here and manipulating these such that my exponentials multiply together. You can think of this as the integral from minus infinity to infinity dxi first, and then the integral from minus infinity to infinity dk. E to the I, combining these two things together, I'm going to get something like kx minus kxi. And all of this is going to be multiplied by psi of xi. Now, if this whole thing is going to be equal to psi of x, this expression right here should look familiar. What function gives me psi of x when multiplied by psi of a dummy variable and integrated over the dummy variable. This function here, this guy, we have a name for it. It's delta of x minus c, or c minus x. So this is sort of delta function. This is what I'm really going to get out of these sorts of normalization conditions. The infinity that it goes to when p1 equals p2 is like the infinity that the delta function goes to when x equals 0, or x minus c, or x equals c. The 0 that it goes to is like the 0 of the delta function when its argument is non-zero. So subject to this version of orthonormalization, that if p1 is not equal to p2, you get 0, and if p1 is equal to p2, you get, well, infinity, but infinity in a useful way, such that in the context of integration I can get functions out that as I would expect. You can prove the same sorts of results for an eigenvalue problem with a continuous sort of spectrum. That's about all that I want to say about these sorts of topics. To check your understanding, let's consider the position operator x hat. Is it Hermitian? What is the spectrum like? Is it continuous or discrete? What are the eigenfunctions of x, the operator? And do those eigenfunctions form a complete basis? So think along those lines, and hopefully that will help solidify this notion of the mathematical formalism that we've been working with in the language of the context of Hermitian. The formal mathematical structure of quantum mechanics can also, of course, be applied to determine the statistics, perhaps, of measurements made of quantum mechanical systems. These notions of statistics appear a lot in the context of uncertainty, for example, variance, and the overall average outcome, the expectation value. So let's consider how the formal mathematical structure of states in a Hilbert space can be used to determine the statistical properties of quantum mechanical systems. What we're talking about here is some observation. So consider just some generalized observation, meaning I'm talking about some observable Q as represented quantum mechanically as an operator, Q hat. We've talked about, over the last couple of lectures, eigenvalue problems. Q hat applied to some state gives me Q, the eigenvalue, multiplied by that state. And we've talked about the results of these eigenvalue problems. Either we have a discrete spectrum, we get some sort of set of psi sub n's associated with some q sub n eigenvalues, from which we can construct, for instance, any arbitrary state f, for example, as a superposition of a bunch of stationary states, or a bunch of states here, a bunch of psi sub n's multiplied by some sort of a coefficient, and we can determine that coefficient with Fourier's trick, left multiplying this overall expression by a particular psi sub I. So a sub I is going to be given by psi sub I f, coming from the left-hand side. The sum on the right-hand side collapses, etc. The usual Fourier's trick reasoning applies, involving the orthogonality of the psi sub n's. We have this nice set of mathematical tools that we can use. We have a set of vectors that forms a complete basis for arbitrary functions. These are orthonormal basis vectors, basis states, and they can be used to construct anything. We also talked a little bit about what happens if you get a continuous set of solutions, not a discrete set. So let me just write this as some arbitrary psi of q. I'll write this as a state. It looks sort of like a function and a state. Think of this as a state that depends on some continuous parameter q. So each value of q plugged into some general structure gives me a distinct state, and I can think about the eigenvalue as q. Under those circumstances, the completeness of the basis states can be expressed as an integral. So I'm constructing the same sort of general quantum mechanical state as an integral over q of some sort of coefficient. Let me write it as f of q, multiplying this state psi of q. So I have some general function multiplied by some general coefficient, and I'm integrating up if I have some sort of continuous spectrum of eigenstates and eigenvalues. This f of q is determined by Fourier's trick using the Dirac orthonormalization of these sorts of states in much the same way. It's again going to be an inner product of psi of q with the state that we're trying to find, or with the state that we're trying to represent, excuse me. Now, given this sort of mathematical structure, can we discuss the notion of measurement, or some sort of an observation? What happens when we measure Q? We've got some sort of device, we've put our quantum mechanical system into it, and it spits out a number. What numbers is it likely to spit out? Well, in the discrete case here, it's actually quite straightforward. You are going to get one of these eigenvalues. This is the generalized statistical interpretation of quantum mechanics. You're going to receive one of the Q sub n's in that set of Q sub n's. I should probably use a different index here. One particular value from that set, and you're going to get it with probability given by, well, if I get value Q sub n, I'm going to get it with probability A sub n squared. So the coefficients that appear in this expansion, this representation of the state in terms of these basis vectors, is really the, well, square root, in some sense, of the probability of receiving each particular eigenvalue. So this is actually quite an interesting statement. When we measure Q in a system with a discrete quantum mechanical spectrum, we always get one of the eigenvalues of the operator corresponding to the observable that we measure. And we get that value with probability given by this very simple sort of formula. You can take the squared magnitude of, essentially what you're looking at here is the part of f that is in the psi sub I direction, if you want to think about it. There is, of course, a continuous counterpart to this, but measurements of a continuous spectrum are a little bit more subtle. You have to think about what it means to observe something, and you're never going to, if you're trying to compute the probability of getting, say, exactly 6 out of a continuous distribution, exactly 6 will never happen. You will only get ever numbers very, very close to 6. But you can think about what's the probability that I get some value Q in between Q0 and Q0 plus some dq. So I've got some sort of interval here between Q0 and Q0 plus dq. If the value that I get falls in that range, then we can represent the probability here. And you'll get it with probability given by the magnitude of f of q squared multiplied by dq. So this f of q, this coefficient that we determine as the result of an inner product with our sort of basis and the function that or state that we're trying to represent, can be used as a probability. This is the sort of thing that we're talking about when we talk about the squared modulus of the wave function as a probability density. The wave function psi of x is really the result of some sort of inner product between eigenfunctions of position operator, which are Dirac delta functions, as applied to the state that we're trying to represent. So that's where the probability density comes from. Now, this is not so much a mathematical result that can be proven. These sorts of, you'll always get an eigenvalue and you get some sort of a probability, or you'll always get some sort of a continuous value, some sort of a value with this sort of probability. Those aren't mathematical results as much as they are sort of axioms of quantum mechanics. This is a generalized statistical interpretation that takes us beyond the notion of the wave function as something that gives you the probability density of position measurements, meaning the probability density of where you're likely to find the particle if you observe the particle, meaning observe its position. So these sorts of probabilities are, of course, going to be useful in the context of computing probabilities, but in order for them to be useful in computation of probabilities, we first of all have to have some sort of normalization. Now, you can think about normalization of a wave function or of a state in the context of these vectors in the Hilbert space as the inner product of the state itself must equal 1. Now, if you think about that in the case of a discrete spectrum, this state f can be written as the sum of some a sub n times some psi sub n, meaning if I'm working with some set of psi sub n functions, some sort of a basis, I can figure out the overall, I can figure out these coefficients and determine the overall state that I'm trying to represent. If you look at this inner product in this context, you're going to have, well, it's an infinite sum and an infinite sum. So I've got some sort of a sum over n of a sub n star, psi sub n on the left, and some sort of an infinite sum over n, or sorry, I should use m, different index, of a sub m psi sub m. And if I distribute these two infinite sums together, I'm going to get psi n, psi m terms. And psi n and psi m, those inner products, obey an orthogonality relationship. I'm assuming these psi sub n's come from the eigenstates of a Hermitian operator. So the orthogonality is going to collapse the two sums together, and I'm just going to have one sum left. I'll get, say, a sum over n of a sub n star a sub n. And the normalization means psi n, inner product is 1. So my wave functions are gone. So this normalization condition here implies that the sum of the squares of those coefficients in the representation of my state is going to be 1. In the language of continuous spectra, what we're talking about here, again, is an inner product. Inner products you can think of as integrals. So we've got some sort of an integral of some sort of f of q squared modulus dq. This is, again, sort of an addition of all probabilities. Well, we've got an addition of probabilities here, a summation of a bunch of probabilities that better add up to 1. This is an integral of a bunch of probabilities that adds up to 1. And this integral comes from the same sort of orthogonality argument as the infinite sums collapsing here. Instead of two infinite sums multiplied together, we would have two integrals, which we could manipulate to get a Dirac delta function in terms of the Dirac orthonormalization of these sorts of basis states, what I wrote as psi of q on the last slide. So these normalization conditions make a fair bit of sense. Probabilities have to sum to 1. We can make some use of that. Another situation where these probabilities are useful is in the computation of an expectation value. So say I want to compute the expectation value of some arbitrary operator q. That, in the language of these linear operators, is f inner product with q times f, q operator acting on f. So here's my arbitrary state f, again, and q being applied to f. So again, I can make these sorts of infinite sum expansions, sum over n of a sub n star, psi sub n, multiplied by an infinite sum over m of a sub m times q acting on f. Sorry, not f. Once again, psi sub m, coming from this same sort of expansion of f and the expansion of qf. So the expansion of qf is going to be q acting on the infinite sum, and I've distributed q into that infinite sum, acting on each individual term. Now, q acting on psi sub m, that was my original eigenvalue equation. Q acting on psi sub m is simply going to give me q multiplying psi sub m. So in the case of calculating the expectation value of some general operator, when you have your general state represented in terms of eigenstates of that operator, is actually quite simple. Again, we're going to get psi n and psi m when I distribute these two sums together. You're going to have a sum over n and a sum over m. I'm going to have an a n, that looks a little bit like a w, a n star, and an a m, and a q. This is technically going to be q sub m, associating psi sub m with q sub m was part of the definition of these psi sub m's. And I have a psi sub n and a psi sub m, which again, I can say this is some delta n m, which collapses my sum down. And what I'm going to get in the end is a sum just over a single variable, let's say n, times the squared modulus of a sub n times q sub n. So this, if you look at it from the perspective of statistics, this is a weighted average. These are the probabilities associated with each observation, and these are the values that are associated with each of those probabilities. You can do the same sort of thing within the context of a continuous spectrum. Under those circumstances, you're going to have, I'll write it out under these circumstances, the expectation value of q for a continuous case is the integral from minus infinity to infinity let's say I've got dq, right, so I'm constructing an integral representation of f. So let's say that's going to be an integral over q1, f of q1. I have to complex conjugate this. So this is my coefficient from the integral, from the representation of f complex conjugated. And then I've got my psi of q1 actual function. And definitely running out of space here. Shift this to the left a little bit. And that whole thing is going to be multiplied by a similar looking integral, except this time I'm going to be representing q applied to f. So this is going to be an integral dq2 to use a different variable. We're going to have a coefficient f of q2, again appropriate for representation of my state. I'm going to have my operator q multiplying my psi of q2. And close my state and close my parentheses off screen. Hopefully that's reasonably clear in terms of at least my handwriting. This is a representation of this, and this is a representation of q applied to that. You can make the same sort of arguments here. Q applied to my state is going to be q2 in this case times psi of q2. That's my eigenvalue operation. And then I have the same sort of double integral becoming a delta function sort of thing as I had a double sum becoming a Kronecker delta over here. So this is going to give me, rearranging the order of these integrations a little bit, integral minus infinity to infinity dq1, integral minus infinity to infinity dq2, and then I've got an f star of q1 and an f of q2 and q2 and an inner product of psi of q1 and psi of q2. It's subject to these Dirac orthonormalization constraints that we have to have in order to make continuous spectra really make any sense. This is going to be a Dirac delta function of q1 minus q2. Applying that Dirac delta function in this integration means I can do one of these integrals, and what I'm going to get is the value of the integrand such that, or that occurs where the argument of the delta function is 0. So if I'm doing the integral dq2, I'm going to get the value where q2 has become q1. So all you're going to be left with is a single integral, minus infinity to infinity, dq1, and I've got an f star of q1 as before, and an f of q, not 2 anymore, excuse me, f of q1. This q2 becomes q1 is basically the whole point of applying the delta function. This is the result of doing a delta function integral. I've also got that q1 laying around from before, and that's it. That's all there is to it. So this, getting a little cramped in the right, is the integral from minus infinity to infinity of that squared modulus of f of q dq multiplied by, sorry, not dq, let's say multiplied by q integral dq. So this is the same sort of expression here as you have here. So squared modulus times the value, squared modulus times the value, properly normalized, given the Dirac orthonormalization and the Kronecker delta sort of orthonormalization of these two sorts of sets. Either we have a discrete spectrum, in which case things are infinite sums, or we have a continuous spectrum, in which case things are integrals. So that's what your expectation values are going to look like. They're going to be sort of weighted averages with sums or weighted averages with probabilities. Or, with continuous functions as computed in integrals. You've seen expressions like this before in, for example, the computation of the expected value of the position operator. This is going to be an integral over position multiplied, an integral over position multiplied by the position multiplied by, sorry, this should be squared, the squared magnitude of the probability density, or of the wave function, f of x. Now, of course, all of this is expressed in terms of some general operator q. So let's do an example. Let's think about measuring the momentum for the quantum harmonic oscillator ground state. Now, measurements of momentum means we're talking about the momentum operator. And we know we're always going to get one of the eigenvalues of the momentum operator, so we have to, in principle, solve the eigenvalue problem. Momentum operator applied to some arbitrary state gives me the momentum, the number, multiplied by the state. And solving that eigenvalue problem is something we've done. You end up with something like e to the I px over h bar divided by square root of 2 pi h bar I think goes in the denominator as well, associated with eigenvalue p. So these are my eigenstates expressed as wave functions, and these are my eigenvalues of those wave functions. Now we talked about these things before. This was e to the ikx over root 2 pi, and this was k h bar. How can we determine, for example, what the probability distribution of momentum measurements is going to be for a particle prepared in the ground state of the quantum harmonic oscillator? Well, we're going to get some value p, and we're going to get it with probability given by the magnitude of some function f of p squared. All right? We're not going to get p. We're actually going to get something between p naught and p naught plus delta p. Running out of space here. But the language sort of makes sense. I have some sort of a probability density multiplied by the size of the interval over which I am accepting values of p from p naught plus dp. That's my sort of probability density. Now within the language of the linear algebra that we're working with, this function f of p is going to be that psi of p function. Think about that as the complex conjugate of this, multiplied by psi 0. Psi 0 being the ground state of my quantum harmonic oscillator. And you can write out this inner product in terms of wave functions, if you know what these things are. Minus infinity to infinity. I'm integrating dx. And I have my psi sub p on the left, meaning complex conjugated. So this is going to be e to the minus I px over h bar divided by root 2 pi h bar. And then I have my quantum harmonic oscillator ground state, and we found that in a variety of ways. It looks something like m omega over pi h bar raised to the 1/4 power times e to the minus m omega over 2 h bar x squared. So I have an integral dx of e to the minus x squared and e to the itx. We've done this problem before. This is computing the Fourier transform, essentially, of your ground state. This Fourier transform is essentially a special case of the sort of transforms that we are making when we compute the sort of coefficients that appear in the expansions or representations of some arbitrary state in some arbitrary basis. In this case, we're working with the eigenstates of the momentum operator. We could also be working with eigenstates of the kinetic energy operator or eigenstates of any other Hermitian operator. They're all going to form a complete orthonormal basis for which these sorts of probability calculations work. So this integral is doable. Not all that difficult. You end up with another Gaussian just as a function of momentum. It's a sort of closed form mathematical expression. So to check your understanding of these sorts of probabilistic interpretations or these probabilistic contexts, the results of, or as they result from the linear algebra in quantum mechanics, suppose you're considering a particle in a box. So we're solving the time-independent Schrodinger equation for the Hamiltonian, which is an eigenvalue problem for the Hamiltonian operator. We get a set of stationary states and a set of eigenvalues. Now suppose I'm telling you that some arbitrary state psi is prepared in this superposition of psi 1 and psi 2. Answer these questions. If you measure the energy, what's the probability of observing one of a couple of different energies? Double check that this shouldn't be F, sorry. I don't know why I always manage to make typos in these check your understanding questions. This should be psi. Is the inner product of psi with itself what you expect it to be? Does it make sense? And suppose I had some general observable with eigenvalues and eigenvectors such that I have some eigenstate G7 which gives me eigenvalue Q7. If I observe Q, write down an expression for what I would expect in terms of the probability of getting Q7 as a result of that measurement. So that's a bit on the statistical interpretation of the formal mathematical structure of quantum mechanics. This basis allows us to construct probabilistic interpretations of way more than just position and momentum. And we'll continue on along those lines far more later on in the rest of the course. Given our discussion of the formal mathematical structure of quantum mechanics, let's think about the uncertainty principle. Usually we're talking about something like delta x, delta p is greater than or equal to h bar over 2 under those circumstances, but can we do better? Can we expand this beyond simple position momentum uncertainty? The linear algebra structure of quantum mechanics gives us a way to do that. What we're talking about here basically is the uncertainty in some observable quantity. Now, I'll leave it general and say Q here, meaning we have some sort of a Hermitian operator Q hat that we can use when we're talking about making measurements. The uncertainty in that physical quantity, usually expressed as the variance, sigma sub Q squared, is expressed as an expectation value. So this outer pair of angle brackets is our usual usual notation for expectation value. What we're computing the expectation of is a quantity that's squared. So this is the mean squared deviation from the mean, Q hat minus the expectation of Q. Now this looks a little bit odd. We have one pair of angle brackets giving us the expectation of Q. That's just some sort of a number. We can determine that before we even start computing. And then we have the outer pair of angle brackets that's going to give us the expectation of this overall expression, Q minus the expectation of Q. Let me simplify the notation a little bit here and write this number as just mu sub Q. So this is the mean of Q. So this is the deviation from the mean squared. This is the average mean squared deviation. That's our normal definition of the variance. Now you can expand this out using our notation for things like expectation values in the linear algebra structure of quantum mechanics. We have some sort of a wave function, Q hat minus mu Q squared, acting on the wave function. So this, as an operator, we've got the operator Q, we've got the operator mu Q. Mu Q treated as an operator just multiplies by mu. It's like saying 6 as an operator. It's just going to multiply the wave function by 6. You can expand this out, psi on the left, Q hat minus mu Q, Q hat minus mu Q, acting on psi. And at this point, you can look at this and say, well, Q, as represented by Q hat in quantum mechanics, this Q hat is going to be a Hermitian operator since we're talking about an observable Q. And Hermitian operators can act either to the left or to the right. So let me take this Q hat minus mu Q, also of course going to be Hermitian because this is going to be a real number, this is going to be a Hermitian operator. The difference is just going to behave itself as a Hermitian operator. Let's have this one act on the left, leaving this one to act on the right. What I get then is going to be the result of having Q hat minus mu Q act on the left, inner product with the result of having Q hat minus mu Q act on the right. So this is just a sort of straightforward manipulation of the expression for the uncertainty in some observable quantity Q. Now, you've got the same sort of thing on the left as on the right. Let's look at this and let's say this is some vector f. And this is, well, then it's going to be the same vector f. This overall here is going to act as just an inner product. F inner product with itself. I've got these two variables, or this vector which happens to appear twice. So whatever this vector is, I hesitate to call it the state of the system, but it is a vector in the Hilbert space as a result of applying a Hermitian operator to a state. And you can write that down. Just this is a definition of f. Now, in the context of uncertainty principles, we can always have determinate states. Any of the eigenvalues of Q, or eigenstates of this Hermitian operator Q, are going to have certain value of Q. So it's certainly possible for sigma sub Q to be equal to 0. But if we have a second observable, that's where we start talking about uncertainty principles. So suppose I have a second operator, or a second observable quantity, R, as represented by some Hermitian operator R hat. I can use that to construct sigma sub R squared in exactly the same way as this, substituting R for Q everywhere in this expression. And when you get down to it, instead of calling that F, let me call that G. So if we have two separate operators, there's nothing to prevent me from making this manipulation for both of them, which means what we're talking about in the language of the uncertainty principle, as motivated by that delta x delta p structure, we're talking about something like sigma q squared, sigma r squared. That's going to be equal to, well, it's this f inner product with itself, g inner product with itself, just multiplied together. This is sigma q squared, this is sigma r squared, this is sigma q squared, this is sigma r squared. That should be fine. So what can we do with this? We've got f and we've got g. This is where things get a little bit subtle. But the overall derivation here is not terribly mathematically complicated. You just have to pay attention as things go past. So we've got this sort of expression. What can we do with it? There are two simplifications that are going to turn this equality into an inequality and convert it into a form that is useful from the perspective of the uncertainty principle. And the first of those simplifications, working with this FFGG expression for two general vectors in our Hilbert space F and G, is the Schwarz inequality. Now, the Schwarz inequality is just a relationship between any sort of vectors like this. It says that if I've got the inner product of a vector with itself multiplied by the inner product of another vector with itself, that inner product is always going to be greater than or equal to the absolute magnitude of the inner product of the vectors with each other squared. You can think about this inequality very simply from the perspective of three-dimensional vectors in three-dimensional space. The inner product then is the dot product, and what this tells you is that the dot product of two vectors squared, a dot b quantity squared, is always going to be less than or equal to the magnitude of a squared times the magnitude of b squared. And if you're used to thinking about vectors like a dot b in the normal sort of notation, you've probably seen the formula magnitude of a, magnitude of b times the cosine of the angle between them. Now, since we're working in an infinite dimensional vector space, things like the angle between them is somewhat difficult to define, but this is the same sort of expression. If I dropped the cosine and made this into an inequality, meaning the right-hand side without the cosine is always going to be greater than or equal to the left-hand side, and then I were to say square both sides here, you would end up with the same sort of overall expression. Magnitude of a squared, magnitude of b squared, magnitude of dot product squared. So that's just an analogy. The Schwarz inequality holds in general, though it's somewhat difficult to prove. The textbook doesn't even bother proving it. So this is the first sort of simplification. We're going to pretend that instead of working with magnitude of f and magnitude of g, we're going to work with the magnitude of the inner product. The second simplification is that if we have some sort of complex number z, its squared magnitude is always going to be greater than or equal to the squared magnitude of the imaginary part of z. This is a very silly sort of construction to make if you think about it, but we can rewrite this in the context of that complex number z. So the complex number z then is always going to be at least greater than or equal to the imaginary part of z. Now the imaginary part of z, where the z is this complex number f inner product with g, we can write that as f inner product with g minus g inner product with f. So this is that number z minus its complex conjugate. Now minus the complex conjugate just flips the sign on the imaginary part, leaving the real part unchanged. So this subtraction is going to cancel out the real part and double the imaginary part. Now if I think about this, this is actually twice the complex part of this number, f inner product with g. So I would have to divide it by 2. And the imaginary part is, of course, going to be a purely imaginary number. So if I divide it by 2i, I'll get a purely real number, and I can stop worrying about the absolute magnitude. This is going to be a result. This result is essentially the same as this. So I have 1 over 2i dividing the difference of a number and its complex conjugate to pull out the imaginary part, cancel out the I, and then I'm squaring the result, same as I would be squaring the result here. So this sort of simplification, putting the overall expression up, tells you what we started with, which was sigma q squared, sigma r squared, is going to be greater than or equal to that final result, 1 over 2i times the complex number f inner product, complex vector f inner product with complex vector g minus inner product of complex vector g with complex vector f. So somewhat complicated expression, and unfortunately it's going to get worse before it gets better. Let's take a close look at what these vectors represent. Keep in mind that our vector f here was defined to be q hat minus mu q, acting on our state psi, and complex vector g was defined to be operator r minus mu r, acting on our state psi. Those were our definitions. So writing this out, let's take this first term first. We've got f inner product with g. That's going to be written out in terms of these definitions. So this is q operator minus mu q acting on state psi on the left, inner product with g, which is vector operator r minus mu r acting on state psi. Now these are Hermitian operators, which means I can take the one that's acting on the left and push it back over to the right. Now that seems a little bit strange. Didn't we just do that step in reverse earlier on? Yes, we did. But it's a Hermitian operator. It's a perfectly valid mathematical expression. So that leaves me with just psi on its own on the left, and then we have this product of two operators, q hat minus mu q, r hat minus mu r, acting on psi, all acting on the right. This is now two binomials. It can be expanded out. So psi on the left, all by itself. And then here we've got something that needs to be FOILed. And keep in mind, operators don't commute in principle. While the operators q and r are not going to commute, mu q, r, and q, etc., those are just mu q and mu r, just multiplication by numbers. That commutes with pretty much everything. So what we're left with, we're going to have a q hat, r hat term here. We're going to have a minus mu q r hat term here. We're going to have a minus mu r q hat term from here. And we're going to have a plus mu q mu r term here. So there's our smiley face. We've accounted for all of our terms, got all of the signs correct. All of that is acting on psi on the right. Now this is just an operator expression with four terms in it, separated by addition. These are linear operators, meaning I can separate this out into four separate expressions. What you're going to have then is going to be psi, q hat, r hat, acting on psi, minus mu q can be factored out of this sort of resulting expression, mu q times psi acting on r hat psi, from the r hat acting on the psi, and mu hat being pull factored out. Likewise, mu r psi q hat psi plus mu q mu r psi psi. So we can simplify some of these terms right away. This guy is just 1. This is the normalization integral. If our state is properly normalized, this inner product is going to be 1. And the rest of these things, these are expectation values. This is the expectation value of q hat, r hat. This is the expectation value of r hat. This is the expectation value of q hat. So if I was to pull along the constants, have them all come for the ride, this is q hat r hat minus mu q, expectation of r hat, minus mu r, expectation of q hat, plus mu q mu r. But r hat, that's just mu r, and q hat, that's just mu q. So I've got the expectation value of q hat r hat, whatever it is, minus mu q mu r, minus mu r mu q, plus mu q mu r. These are just scalar multiplications. They commute, so one of these is going to cancel out. Let's say that one. And what I'm left with is the expectation value of q hat r hat minus mu q mu r. So that's what I got for fg. Now fg, I've also got to work with gf. Gf is going to end up very similarly. If you think about g and f, it's going to look essentially identical to this, except q and r are going to be interchanged. So g and f here is going to give me the expectation value of r hat q hat minus, again, mu q mu r. Same sort of product of uncertainties, or product of means. So that, believe it or not, is all we need to get our main result. We have sigma q and sigma r in terms of these sorts of complex numbers, which are expressed in terms of expectation values of those fundamental operators. So if you substitute all of that back in, we had fg minus gf. That's going to be bracket q hat r hat, so expectation of qr, minus the expectation of r hat q hat. And that's it. The mu q, mu r terms are going to cancel out. They were added on regardless whether we're talking qr or rq, so when we subtract, they're just going to cancel out. And you can think about this as being the expectation of q hat r hat minus r hat q hat, which this qr minus rq, you should recognize this is a commutator. So we can write this down instead as the commutator of q hat and r hat. So, our final expression then, putting all of the constants back into it, is that sigma q squared, sigma r squared is always going to be greater than or equal to 1 over 2i times the expectation value of the commutator of the operator q with the operator r. All of that squared. That is our result. That is the generalized uncertainty principle. What this tells you is that any two operators, q and r, are going to have an uncertainty relation if they have non-zero commutator. So if the two operators commute, there's nothing wrong with knowing both of them precisely. They can both have zero uncertainty. But if they have non-zero commutator, meaning the expression qr minus rq does not have zero expectation value, then any two observables then those two observables will have non-zero uncertainty principle. There will be some minimum uncertainty. The obvious example to do here is position and momentum. We talked about the commutator of the operator x hat and the operator p hat before. It's just x hat p hat minus p hat x hat. And if you substitute in the definition of p hat as minus I h bar partial x, and the definition of the operator x hat as just x, multiplied by, and you insert some dummy wave functions on either side, that was an activity that we did earlier on in the course. You find that the commutator here is equal to just a constant, I h bar. It's a complex constant, which seems a little strange, but there's nothing wrong with complex numbers when you're mixing operators like this. It's only when you would make an observation of a single operator, single physical quantity, that you have to get real numbers. What that tells us is that sigma x squared sigma p squared in the generalized uncertainty relation is going to be 1 over 2i times the expectation value of the commutator, which is just I h bar squared. So the expectation value of a constant is just going to be the constant. So this is just going to be I h bar over 2i quantity squared. I's cancel out, and we've just got h bar squared over 4. H bar over 2 squared. Now the way that uncertainty principle is usually stated is sigma x sigma p is greater than or equal to h bar over 2, and that of course is clearly the same expression that we're working with here. So good. We've got the same sort of uncertainty relation that we introduced earlier on in the course. To check your understanding of this sort of process, here are some questions for you. What would happen in the derivation if instead of throwing out the real part, meaning instead of saying that the absolute magnitude squared of some complex number is always greater than 1 over 2i z minus z star, all squared, what would happen if I instead threw out the real part by adding the number to its complex conjugate instead? Would you still get a commutator, and what extra terms would it introduce? And finally, just in terms of some of the steps in that derivation, why exactly did this step happen? What are the principles that are applied in that equality? What definitions do you need to know? Now that's about all that there is to the generalized uncertainty principle. It's an amazingly powerful mathematical tool, but well, let's play with it a little more. How strict is this limit, and can we beat it? Now the limit that we're talking about here is this relationship. I had some sort of sigma q squared sigma r squared was always greater than or equal to 1 over 2i times the expectation of the commutator of operator q and operator r, all squared. That's our generalized uncertainty principle. This inequality, where did that inequality come from? Well, it came from two places. It came from the Schwarz inequality, which told you that the inner product of that vector we defined, f with itself, multiplied by the inner product of the vector g with itself, was always going to be greater than the squared modulus of the inner product of f and g. That was one source of the inequality. So if we're trying to make this into an equality, we have to not grant any space in between the result of these inner products and the inner product of the vectors with itself. How can we make the Schwartz inequality into an equality, in other words? And that's rather straightforward if you think about it. The vector g is just going to be some constant, say c, times the vector f. If this is true, then this is going to be c squared f squared, and this is going to be c squared f squared, and we're going to have an equality here overall. The second inequality we had was when we threw out the real part. We said the magnitude of that complex number, fg, in terms of its squared modulus, was always going to be greater than or equal to this 1 over 2i times fg minus gf. All of that squared. This statement, can we make this into an equality as well? Well, what we're looking at here is going to be an equality if we're throwing out the real part, and we're taking the squared magnitude of it. The squared magnitude is only ever not going to change when we throw out the real part if the real part is 0 to begin with. So we've got equality here if the real part of fg, that inner product, is equal to 0. And that's reasonably straightforward. We're looking at fg, but we know g can be expressed in terms of c, so we're talking about the real part of f times g expressed as cf gives me a c and another f. So the real part of c times this inner product of a function, or of a vector with itself, this inner product of a vector with itself is going to be a real number. No matter what you do, you're taking a complex conjugate, multiplying it by itself, essentially, you're going to get a real number. So this is only ever going to equal 0 if c is complex. C is, purely imaginary. C being purely imaginary, let's write it as the imaginary unit I times some real number, A. So given some C equals I times A, if we define our states, or if we define our operators and our states such that G is given by some complex unit times A times the state F for, some real A, then we've turned both of our inequalities into equalities. So what does that mean? What sort of implications does this have? Let's consider that in the context of position momentum uncertainty, just to make this a little more concrete. We have this notion that our vector g is imaginary unit times some real number times our vector f. Now in the the language of position momentum uncertainty, then this vector g is going to be p hat minus expectation of p times our state. And we know what the position, or what the momentum operator is. This is going to be minus I h bar, partial derivative with respect to x, minus expectation value of p. I'll just leave it as expectation value of p here. This is just going to be a number, so there's no magic there. And this is going to be multiplied by psi of x. If I'm writing out my momentum operator in terms of partial derivatives, I better write my wave function in terms of x instead of just as some arbitrary state vector. Likewise, we've got our vector f, and this has to be expressed in terms of our position. So this is going to be x hat minus expectation of x, acting on our state. And likewise, in terms of wave functions, this is going to be x multiplication minus expectation value of x, the constant, multiplying our wave function psi of x. So our expression for g in terms of IA times f, with these particular definitions of g and f, we can plug these together, substitute these expressions here into this equation here, and you end up with, separating things out, minus I h bar partial psi partial x minus expectation value of momentum multiplying psi and that has to be equal to I times A times our expression for f, which, I'll just expand that out. We've got I times A times x times psi of x minus I times A times expectation of x times psi of x. This right here is a differential equation for psi. And it turns out it's actually a pretty easy differential equation to solve. If you rearrange things a little bit, you can find out that this is going to give you a derivative of psi with respect to x as, in terms of, let's see, what have I got? I've got a, after I've divided through by minus I h bar, I'm going to have a minus a over h bar, let's say x psi, pulling the complicated term first, and then I'm going to have a plus a over h bar expectation of x psi, and a plus I expectation of p over h bar psi. Provided I've got all of my signs correct there, and I haven't lost any terms, I've got the over h bars. Yeah, I think that looks right. This is a fairly straightforward ordinary differential equation to solve. Now, I'll leave it as an exercise to you guys to actually go through and solve this, but the procedure for solving it, I think is most easy to think about. Let me just guess that my wave function psi is equal to e to the some sort of function f of x. If you do that, you find a simplified differential equation just for f. This sort of initial guess where psi is going to be some sort of an exponential and you're trying to find the behavior of the exponent is a common technique for solving differential equations where your derivatives essentially give you the function back multiplied by various terms. Under these circumstances, you can figure out what your psi of x actually looks like. And your psi of x under these circumstances has to be e to the minus a over 2 h bar, let's see, x minus the expected value of x, quantity squared, e to the I expectation value of p over h bar times x. And then there's another constant floating around here, something like e to the a expectation value of x squared all over 2 h bar. This solution comes out of just a straightforward solve here. The only simplification I've made on the result is to complete the square in the exponent. Whenever you have a x squared sort of behavior, it's good to pull that off by itself. The reason I've separated these three terms out instead of writing them all as sums together in the exponent is it makes the structure a little bit more straightforward. This is some sort of a constant. This is something that looks like just something with a certain momentum, ikx. And this is a Gaussian. E to the minus something x squared. This Gaussian form is definitely a realizable wave function. We've actually met Gaussian wave functions before, for example, in the quantum harmonic oscillator ground state. Under those circumstances, you have met the uncertainty limit. You can meet the uncertainty principle limit, so the two messages there is, first of all, the uncertainty limit is attainable, but it's difficult. You have to be in a very specific sort of mathematical state. This is not going to be true for anything that's non-Gaussian. The second take-home message from this is that the uncertainty principle is actually a fairly strict limit. That despite the fact that we made those seemingly a little bit fudgy simplifications when we were working through the derivation of the generalized uncertainty principle, applying the Schwarz inequality, and just assuming that the real part of the number could be neglected and the imaginary part was the only thing that mattered, we haven't actually ceded too much ground there. The uncertainty principle is a fairly strict limit that is actually attainable. It's not like we've made some ridiculous lower limit, or ridiculous lower limit on the uncertainty. Regardless, that's a mathematical discussion of the formal structure of the uncertainty principle in quantum mechanics, and subject to the generalized uncertainty principle, any two operators with a non-zero commutator are going to have some sort of uncertainty principle. And you could go through the same sort of derivation of what the minimum uncertainty behavior would look like for any two operators. It's relatively straightforward for the position momentum structure, and you get a Gaussian, but you could do it for other cases as well. I think that about sums it up, though. Generalized uncertainty in quantum mechanics is, like I said, a very powerful mathematical tool, so keep that one in your bag of tricks. Given the generalized uncertainty principle for any two quantum mechanical operators, something like sigma q squared sigma r squared is greater than or equal to 1 over 2i times the commutator of the operator q and the operator r, all squared, you might think that uncertainty principles have been pretty well settled. But that's actually not the case. While this does give a good and satisfying explanation of something like the classic sort of delta p delta x is greater than or equal to h bar over 2 sort of uncertainty relation, it doesn't cover the case delta e delta t is greater than or equal to h bar over 2. If you've seen this sort of uncertainty principle, it's also very useful in physics, but it is of a fundamentally different nature than position momentum uncertainty. And the fundamental reason for that is that there's something special about time. Time in quantum mechanics is a parameter that shows up in the arguments to your equations. It's not so much like momentum where there's a well-defined momentum operator. So how can we handle energy-time uncertainty? Well, the notion of time in a quantum mechanical system is a little bit squishy. If you're talking about the time evolution of something like e to the I e t over h bar, that solution to the time-dependent Schrodinger equation, or at least the time part thereof when you apply separation of variables, this thing just rotates around in complex number space. It doesn't actually change the fundamental nature of the solution unless you have some sort of a superposition of two states where they have different time dependences, two states of different energies, and the overall time dependence only ever depends on the energy difference. Now, that suggests that if we're talking about some sort of a change in a process, some sort of a change in expectation value of position, for instance, that as it results from a superposition of two stationary states with different energies, we have to consider the notion of change. Time is only ever going to be relevant when we're considering things that change, because if nothing is changing, then what does time really mean? Well, if we're talking about change, we're talking about some sort of an operator, because we're talking about something that changes. We need to have an observable, so we need to have some operator, and as usual, I'll call that q hat, meaning the Hermitian operator that corresponds to some sort of quantity q. So let's consider time derivative of the expectation value of q. This gives us some sort of classical almost notion of how things change with time. Now, the expectation value in our generalized linear algebra formulation is an linear product of our state psi, our operator q hat acting on state psi. This inner product has three components to it. We've got a wave function on the left, an operator, which potentially has time dependence in it itself, and another wave function on the right, or another state on the right. And if you think about the inner product as written out in terms of an integral of wave functions, this is going to be a complicated integral, but it's got three things in it that are all going to potentially vary with time. So let me sweep some of the mathematical details under the rug here and rewrite this, more or less applying the product rule. So we've got a partial derivative of psi with respect to time, whatever that state may be, multiplying our inner product with q acting on psi. We have psi on the left acting on a partial derivative of q hat with respect to time, whatever that may be, that operator acting on psi, and we have psi acting on, or inner product with q hat acting on partial psi, partial t. Now, this is a very suggestive notation. It feels like it's only ever going to be relevant if we're talking about psi as functions of time. What on earth does this notation mean to begin with? Not much, to be quite frank with you. There's a lot of somewhat dicey mathematical things that have happened behind the scenes in applying the, quote, product rule, unquote, to this sort of expression. If we're really going to write these things out as integrals, then these are well-defined mathematical operations, and you can apply the product rule, and all of these sorts of things make sense. But if we're trying to do this in general, I've kind of swept a little bit too much under the rug. That said, I'm going to leave things in this general form. And the reason for that is it's a much more concise notation. So if you want a sort of behind-the-scenes idea of what's going on in each of these terms, try and translate it into an integral and figure out what exactly has happened in each of these steps. If you're willing to take me at my word that this is at least somewhat meaningful notation, we can write down, for instance, some of these terms with partial derivatives of psi in them can be simplified with the time-dependent Schrodinger equation. And the time-dependent Schrodinger equation tells us that I, h bar, partial psi, partial t, is given by the Hamiltonian operator acting on psi. So really I ought to say this is a state, and this is a state in my vector notation. But in this sort of context, you can simplify this sort of term and this sort of term. So let's do that. Let's substitute in for this and in for this. When you do that, these three sort of expectation value-like terms can be simplified a little bit.